Welcome everybody for, can you hear me?
Yes.
Yes, okay. It's very good. So it's really a pleasure to be together, even in this online format. And thanks for all the PhD students and board members to joining in. I'm sure there will be more people joining during the day. But I would say let's keep going because we have a very dense morning. Let me only recap the purpose and the rule of the game. First of all, thanks Joanna, Miliu, and Vittorio Romano for organizing the event. We have proposed to go with a agile format. Each of the PhD students from that are completing the first year have allocated 20 minutes to be used, around 15 minutes for presentation, and please leave at least 5 minutes for questions and suggestions. What is the purpose for today's meeting? As any other edition, we have more or less to this time of the year a presentation of the ideas for the PhD project to be spelled out. At this moment in time, the 10 PhD students for this year edition have more or less their supervisors set. They have quite clear ideas on what kind of research challenges they would like to pursue. Now the point is to refine them and to make them as concrete as possible, as challenging as possible in the PhD thesis proposal that is due September. And also use this moment in time also to make up the panels who will follow, the individual panels that we will follow the students during their PhD. Okay, so this is the purpose of the day. I would not say more than that for the moment, and I would like to ask the first who's Lorenzo, if I'm correct.
Yes, it's me. Good morning. Can you hear me? Can you see me?
Yes, Lorenzo, the floor is yours.
Yes, but I can't share the screen. No, I can. Never mind. Sorry.
Go ahead.
Can everyone see my screen in presentation mode?
Yes, perfect.
Yeah. Okay. Sure. Okay. Good morning, everyone, and I'm happy to be the first one to actually present in this PhD day, and today I'll be briefly sketching over the main challenges we have ahead with the PhD project of which I will be tackling on for the next 2 years, and the progress we've made in the past year, which is something that must be noted. The main aim of this project is mainly to enrich current NLP techniques with domain-specific knowledge, domain-specific information, I'd say, by exploiting structures, mainly exploiting the knowledge graph's data structure, with two main applications in mind, which are to biological networks and newsfeed. So first of all, I need a little bit of background for those who might be unaware of what is a knowledge graph. It's a data structure, a graph basically, where nodes are real-world entities, like, for example, people, location in the world, stuff like that. And relationships between them are labeled with the kind of relationship those two entities hold, in a sense. So, for example, this person lives in this place, and stuff like that. There are several applications of data structures like this. The most notable one are those Google search info boxes. So, for example, if I type a person on Google, I get these small info boxes, which are actually information that are mined directly from the knowledge graph. So There are, of course, several applications that can be done. Our most interesting one, in our opinion, is the one of information extraction. Let's say I have a text, like, for example, the one shown in this slide, and I have a back-end knowledge graph. In our case, for example, the Wikipedia knowledge graph, which is an open source one, an open access one. So what does the human mind do to actually understand what concepts are in this phrase? Well, the idea is the following. I read Leonardo, and I know that there are several Leonardos in the world, but the one that is referred to in here is Leonardo da Vinci. How? Well, because of related entities and context, in a sense. So I read this phrase, I understand the concepts, I understand the related entities in this field, and so I understand that this Leonardo, an ambiguous phrase, refers to Leonardo da Vinci. And this is actually what algorithms do. There are several entity annotators, both developed here in Pisa and not, and they all do basically the same. They understand the topics by mining them on the knowledge graph by means of related entities in that phrase and context. This is a very powerful toolbox in a sense, because it also allows us to expand the concept of phrase similarity with the use of entities by extracting them from text. So I get a more powerful sense of strong semantic similarity in a sense. Let's see those two examples, which are phrases which are very syntactically different, but refer to the same sphere in a sense. With the concept of entity extraction, I can actually extract those entities and map them to, for example, to a Euclidean space using concepts, machine learning concepts like entity embeddings, and actually compute similarities between them, which are in a sense macro similarity. For example, I may get Michelangelo Buonarroti and Renaissance being very closely linked together and stuff like that. And I can mine from this subgraph information such as semantic similarity. It's a very powerful toolbox, but it's usually not enough, in particular in domain-specific application. I'll show you an example. Let's say we have this situation in which we have two news pieces, one from the left and one from the right. Those are two clearly declared newspapers. These are all articles talking about the same concepts, which are transgenderism in minors. It's a very interesting concept, of course, very interesting and very polarizing topic. And if I algorithmically treat those two news the same, I would get something like, yeah, those two articles are actually very similar, but they're not, of course, because in the concept of news, polarization, in particular of concepts, is very, very important. Well, I can algorithmically treat those two the same. They talk about the same thing, of course. But in a view of a socially responsible AI, this is not something we can do, because filter bubbles and polarization are something that must be treated algorithmically. So they must be taken care of during the algorithm stage, not later. So this is our idea. Enrich this news, these NLP information extraction tasks with domain-specific application. In our case, political bias, not only political, of course, but we exploit, for example, tools such as Eurotopics, which already contacted, which gives us political leaning of newspapers from all around Europe. And we actually use them to estimate the political leaning of news articles, which is something very important. Of course, the only sources of bias are not only political leaning, there are also geographical features, temporal properties, topics discussed, which make also part of the bias, but it's all part of this. So why do we care at this point? Why do we have to treat algorithmically this type of stuff? So the main reason is filter bubbles are a real problem. It has been proven and shown in several sociological studies. This is an example from the 2016 elections from Clinton and Trump. And this is a snapshot of a Twitter social graph. As you can see, people who are, in a sense, Trumpist, while people from the left tend to only follow one of their interesting view, in a sense. So people who follow Trump only see Trump's tweet, and people who follow Clinton only see Clinton's tweet. And it's even more evident, this problem, when we actually deal with journalists. This is another snapshot of the same network, where in orange we can see highlighted the links between journalists and regular people. And we can see that journalists are completely detached from both the real Clintonists, but less, and more importantly from Trump supporters, which also shows why journalists predicted Clinton to win. They had no real link with Trump supporters. This is something that must be taken care of, because people, also journalists are facing the problem of filter bubbles, which means they only see part of the content, which is very important. And what does Google News do in this field? Well, to be fair, not much. The idea is the same with every recommender system. They use mostly syntactic and semantical features at the beginning, and then whenever you're profiled, you get like more and more increasingly news for your political view, in a sense, which makes sense, but also is not very socially responsible. So what was our idea? Well, we need first of all, we want to build a recommender system that minimizes bias. And for that, we need a classifier which identifies the political bias of news. And for that, we need a dataset. So the first thing we did was actually to try and build a USA dataset with labeled news with their political leaning. And we built this, and we also built a recommender system, which was not a recommender system, sorry, a classifier, which was performing quite well. We then moved to Europe, which is a field which has significantly less research. And we have built a classifier. We have an 8 million news data set for that. We are currently still cleaning it, but it's looking promising. We have news from all the countries around Europe except for one, Hungary. And we have labeled it with the political leaning of the news sources using Eurotopics. And we also have a strong connection in this field, which can be useful, which is the one of the European Broadcasting Union, which are a consortium of several broadcasters from all around the world, mostly focused in Europe, and who are currently releasing a news portal, which will be releasing in the next few days, actually, which mostly focuses on accessibility. It's something that we really can also try and push our own ideas in, which is very interesting in our opinion. So the main researches and challenges in this field, the one of news, is the following. First of all, of course, we have to move to a European setting, which means multilinguality, spread out geographic landscape, which is interesting, challenging, of course. And this is the main challenge we'll be facing for the first part of the PhD project. And then we'll be moving to the recommendation part, recommendation and clustering part. Those two will likely mostly have two challenges, which are temporal properties, which of course nobody wants to read the 8 months old news, which makes us have to be very careful with data. And then of course the backfire effect. Let's say I'm a left-wing user and I get proposed the right-wing article. If the polarization of me and the other article are way too much opposing, in a sense, I will only increase my polarization level, which is a proven fact from sociological studies. And this is something that there are several problems like this, and we have to face them algorithmically, which has not been done yet. So it's something that we'll need to take care of. And then, of course, at this point, we have a recommender system, a clustering gathering. We can do several things, like, for example, of course, test it on real people on the EBU platform. Study the impact of, for example, topic or temporal evolution of a topic in Europe, something like that. We can do several studies on this. We can also build a whole news analytics platform, which can be quite challenging, of course, but it can be very interesting. And the other field that I wanted to show you a glimpse of is the one of biology, where we have a very different settings, in a sense. In the first part, we had like many entities, because of course, everything in the human world is an entity, and one ontology, Wikipedia knowledge graph. Here we have a different settings. We have several ontologies, basically one for every disease you can imagine, but very few entities and very, very few types of entities. Genes, protein, drugs, a few more, nothing more than that. So we have actually a preliminary result on this idea. The idea was the following. We have tools such as TagMe, which have been developed for the task of entity linking. They use one backend knowledge graph, the one on Wikipedia, and they extract entities on top of text. Well, our idea was to adapt this concept to biology. We actually built this tool called NetMe, which does the same thing but built for biology, and it uses a backend of several ontologies. It's much more noisy in a sense to handle several ontologies, which makes us have to be extra careful on the annotation phase. But of course, we also need the relationships between edges, which have to be mined from text. And this tool actually performs quite well. We have done several tests also with the help of biologists, and it actually creates several interesting biological networks, which are something that is very, very used in the field. And our goal with this is a research goal for the next few months probably, is to actually take PubMed Central, which is a huge paper hub for biology, and apply NetMe to this and build the whole knowledge graph over the whole papers of PubMed Central. And this is, of course, a challenging task because papers tend to be very noisy and we have to handle several ontologies. But we think that having NetMe as an extra domain-specific application of TagMe, in a sense, can be strong. Also, given the fact that we have already shown interesting results on small networks. Now, this is the immediate research goal for us. Well, then, of course, there are several other research plans and challenges. The first one is to improve the annotation process. And for that, we have connections with experts for biology, which can actually make sure that our networks are the best they can be, and add more ontologies. The more ontologies we add, the more powerful the annotation process can become. And then on top of that, we want to build this knowledge graph over the whole PubMed Central. And then we want to do lots and lots of network analysis. There are several tasks that can use this, like, for example, gene repurposing, pathway reconstruction are all things that are very, very used in biology. And they are very, very interesting to biologists. And we have several requests from that. So it's a very interesting field. And I'd like to leave a conclusion slide with the main research goals we have planned for this next 2 years. While I'd ask if there are any questions, because otherwise I'd stop here. Thanks,
Lorenzo. The timing is perfect.
Okay.
Do we have any questions from the audience? Of course, anybody can speak up. We are in a...
Just a curiosity. I don't know if you can hear me.
Yeah, I can hear you.
Yes, we do.
Okay, so coming to your first application about the politically oriented news pieces, I was just wondering whether there are maybe rare cases where there is some media outlet that, say, strives to remain independent, or I don't know, where you have these journalistic agencies that they simply collect pieces of news without giving any political interpretation.
Okay.
So in cases you don't have a definite label for the political orientation, how would you deal with those items?
Okay, so we actually have several newspapers for which we don't have political label, because we only take those from Eurotopics. We decided to take Eurotopics as gold standard in a sense and use that as a ground truth, we would imagine. So of course, anything that is not in Eurotopics will not have a political label. As of now, we are building a classifier with only those. We are trying to make sure that the test is as clean as possible so that we actually have a classifier that can actually be generalized to other text pieces. And this is actually a challenging part because we really need to be effective on labeling the less biased articles in a sense. So which is why we are trying, the research right now mainly focuses on classifying left articles and right articles. We are trying to be broader with the spectrum, like extreme left, left, center, right, extreme right, something like that. And we actually have to be extra careful to actually be able to identify as much as possible the center part, because it's the most important one with respect to bias-free recommendation because of several links. So as of now, we are I'll get back to it. Give me a second. Okay, see, we are using only the labels we have, but we are trying to build a generics classifier, which doesn't require the journalistic label, of course.
Yes, I mean, just algorithmically, even assuming that all that you have classified is classified correctly, but then when it's going to be operating, I imagine you also want to include potential, let's say, label-free items.
Yeah, sure.
And then the question is whether you're then planning also to incorporate that algorithmically later on.
Okay, yeah. We certainly want to incorporate it algorithmically. We still haven't talked about it as of this stage currently, but yeah, surely.
Okay, thanks a lot.
Sorry, I mistakenly understood the question. No problem.
Thanks, Diego. Any other questions or comments? Of course, just a comment. It's very ambitious objective, and of course, one of the key big issues in this kind of research is finding meaningful way to evaluate, let's say, its impact on real users, and that would be probably the most challenging one, not the only challenging, but a very challenging part of this research.
We are lucky we have on the two fields, we both have very strong connections, which can actually be valuable in the sense of evaluation, which is something that we are looking forward to.
Great. I see also a comment by Joanna. Oh, no, it's just a comment that is a very relevant, very interesting work. Thank you.
Thank you.
Okay, I think we can proceed to the next presentation. Now we have Andrea Pugnana, talking about causality and fairness. Please, Andrea, the floor is yours.
Okay, good morning to everyone. I'll share my screen now. And so I guess you can see it in full view mode, right?
Yeah.
Okay, perfect. I'm Andrea Pugnana from first year PhD student, of course. And today I'm going to talk about my research project, which is called Causality and Fairness in AI-driven Dynamical Systems. My supervisors are Professor Salvatore Ruggeri and Professor Francesco Chiaromonte. I am also part of the KDD lab, and that's it for now. Today the agenda of this presentation will be, very briefly, I will introduce you to the problem, and then I will try to explain my first steps towards the solution, or at least something similar, and then potential next steps and research questions that arise so far. Okay, so the problem is simple, meaning fairness is becoming crucial in artificial intelligence. And why is that? The point is that artificial intelligence systems are becoming more and more involved in our daily lives. And often decisions are taken based on some suggestions coming from artificial intelligence algorithms. There are several examples of this, and especially of unfair algorithms. For probably the most notorious case is the Compass algorithm, which is basically a tool that is used by judges in the real world in order to predict the chances that some person might commit crimes again. And as a fact, in 2016, there was a very popular article called Machine Bias, which tried to study the usage of this tool, and now it worked. As a fact, this is a simple graph that basically tries to plot the distributions of scores for committing crimes based on the people's race. For example, white defendants had these very skewed distributions, where mainly the vast majority of them were considered not so much likely to commit crimes again. And as you can see, the shape is very skewed. However, when we moved to Black people's risk scores, the things became much more uniform, meaning that on average, the average Black guy receives a score that is way higher than a similar white person. And this is, of course, a problem because this is something like a discriminatory behavior from an algorithm, which as an idea, it should be as fair as possible. There are several other contexts where this can apply, and these contexts are typically based on three main parts. There is an individual that belongs to a group, or mainly there might be just a group, and then this individual is somehow scored by an AI decision system. This score is then used by a decision maker in order to take some decisions. And what happens here? In this context, it's important to be fair. But what does it mean to be fair? There are several definitions, and they come from very different fields. For example, economics has certain ideas. There is philosophy that was involved in defining what is fairness. But there are several works that point out that it's not possible to satisfy all the definitions at the same time. Despite this is one very problematic point. But generally speaking, the idea of fairness is that decisions should not be based on sensitive attributes. When I talk about sensitive attributes, I refer to something like gender, like race, age, for example, political party affiliation. And whenever these attributes are not relevant for the decision-making, this is, of course, a problem if I base my decision on this. Another problem that arises is that typically the fairness measures that are used are built on simple statistics of a data set. And so they just capture correlations. It's one of the first things you learn from Statistics 101 that correlation doesn't mean causation. And in this sense, there was some efforts in the last years in order to incorporate some causal reasoning over fairness claims. As a fact, there is a seminal paper in 2017 called Counterfactual Fairness. And what does it mean what is this idea? I provided this simple example. Let's imagine there is a cat that is applying for a shelter. And in order to apply for a shelter, he has to be scored by an artificial intelligence system. Yeah, the idea is that there might be some historical data on this cat, maybe his behavior, maybe he likes or not mice, but also there might be some ideas concerning the fur of the cat. And let's say for this case that the cat is an European cat, and this causes a negative decision for his application for the shelter. Now the point becomes, what would have happened if everything being the same except for the fur of the cat. If he were a brown cat, would have the decision be the same? And this is an idea of counterfactual fairness, because we try to replicate the same process that as humans we have into the idea of a fair decision making. But still there is something missing here, because in the general framework, as this one depicted with the cat, there is just a one-shot scenario, meaning we have the data about the cat, and then we just ignore what happens in the long term, because this decision is we have the data, we have the scores, and we just evaluate what happens. But typically, these decisions are self-reinforcing, and therefore there is a sort of a problem that is the so-called feedback loops. As in real-life scenarios, there is a dynamic involved. Let's think, for example, to a guy that is applying for a loan. If he is rejected, probably it's because he received a low score, but then he will try to improve his score. And this process is ongoing. It's not just a one shot. And there are also other examples, for example, in predictive policing. And just to explain it a bit better, I'll provide this simple example from Lumen Isaac in 2016. Let us imagine we are a police department. And since we have limited budgets, we have to decide where to send police over days. In this case, we talk about, in this example, we talk about arrests due to drug usage. So these are drug-related crimes. And as you can see in Berkeley, we have this historical data of arrests, and they are typically located just in the area number 1, which is there. While through the coastline, it seems that there are not so many arrests. However, if we use some external source of data, we can try to estimate the true crime rate. And apparently the users of drugs are not just located in the city center of Auckland, but it's through all the coastline. And now, what is the problem here? Let us imagine we have a predictive policy tool, such as PredPol, which is vastly used by the police in the US. And let's imagine that we just train that on historical data. This is actually an exercise that was performed in this paper I was referring to. And the experiment was the following. Let's say that we have several dates over a year. And for each date, I'll try to train my model with all the historical data up to today. And then I'll try to predict where to send the police in the day after. And I'll do this for all the days over a year and a half. What happened is that the predictive policing tool sent police patrols just in the city center because of the historical data on arrests. And this is likely a feedback loop problem, because the more arrests I will see in a certain area of the city, the more likely I will send more patrols there. But the more patrols I send there, the more crimes I will likely find in the next period. And this mechanism is self-enforcing. And so this is actually a concern. The goal of my project is to study this problem, but from a fairness point of view, in this dynamical context where the decisions are actually self-reinforcing. And there are very few works in the literature that try to address this. To the best of my knowledge, the only work that has tried to do something similar is a work from last year in 2020 by Krieger et al., where they actually tried to exploit a full knowledge of a causal model in order to shape the relationships among the variables and to tackle fairness concern over this. However, this is just a first attempt, and therefore there is a lot of work to do over this. And as a fact, the first step of my research project was to review the current literature over fairness and causality. Concerning causality, I am also involved in a project, a human AI project called Causality and Explainability in Temporal Data, where together with Professor João Gama and Rita Nogueira from Porto, and also with Professor Dino Pedreschi, and Salvatore Ruggeri and Fosca Giannotti, we tried to work on a repository for causal data sets and tools. And actually we are drafting a survey that tries to, let's say, sum up all the knowledge so far in the causality world. And this is the first step. After this, there are obviously several questions that might arise. And for example, the first one is, can we develop tools that exploit the causal dynamics I was talking about previously in order to simulate policy interventions and tackle the fairness concerns that these interventions might create? After this, the question becomes, in the literature so far, all these tools have been used for very small data sets or simulated data. What happens if I move in a real data set where we have several problems of noise and the dimensions might be very huge? This is something that we need to understand. What are the characteristics that make the data set eligible for our methodology? And well, probably the last question that arises so far was all this methodology requires a knowledge of the causal model, but often this model is missing. And in order to exploit these methodologies, we can maybe use causal discovery techniques to improve the fairness reasoning. Said this, I am probably other questions will arise in the next months. And for now, this is it. And I hope you have enjoyed this and everything was clear. And so I thank you a lot for your attention. And if you have questions, I will try to answer.
Thank you, Andrea. Any comments or suggestions or questions from the audience for Andrea? Andrea is a very ambitious, let's say, question.
I can try to ask a question. Forgive me. I am very environmentally challenged right now because I'm trying to follow this from a corner. I can't make stuff work. It's a bit of a mess. But Andrea, do you want to elaborate a little bit more on what you think are the effects of noise and dimensionality? Can you delineate some kind of difference between what the effect of noise may be or what the effect of dimensionality may be, whether they sort of pile up on top of each other in a more than additive fashion? Just if I don't know how deeply you thought about this stuff, but I was curious if you had already given it some thought.
Well, this is thanks for the question. Well, this is actually not so easy to answer. And I think that it might depend case on case, because so far, for sure, if we miss the causal, the knowledge of a causal graph, a lot of techniques have issues when we deal with large data sets. Due to potentially there are problems with computational efficiency, there are problems with correlations that might arise. It's very difficult to disentangle these effects, but hopefully we will find something. So far, the idea is that the size of the data set makes it computationally difficult, while the noise component makes difficult to find the actual causal relationship, because typically these tools work on independence tests. And after you might find that two variables are independent, but then you are not able to direct the variables, how they interact, whether one is the cause, whether one is the effect. And so this is a tricky question. And up to my knowledge, there is very few work on this. And then there is especially some concerns when you use mixed kind of data, because some techniques work just for continuous data, some techniques work with mixed data, with discrete data. And when you combine both of them together, either you discretize. There is a lot of things that can happen. And yeah, this is also a potential question we can try to address in this line, let's say, and in this project.
Grazie.
Andrea, this is Giovanni Comandè.
Okay.
Fascinating work, and you listed a number of elements that you factor in as not being fair. Just a caveat, we can talk later if you want, but I mean, there are various elements which have different legal bases with different implications in terms of the notion of fairness. So some of them are plainly legal, as we saw in the courses. Yep. Some others are just elements which go beyond law and still can be considered unfair. And this, do you think that these different elements can affect your research questions on fairness?
In a sense, I think so. Like the point is that there are several definitions of fairness, and so we might try to disentangle these two effects, like what is potentially legal and what is not actually legal, as we saw in the course. And of course, this is another aspect that this research can incorporate together just to be more complete and as multidisciplinary as possible, I think. I don't know if this answers.
I believe that Giovanni's remark is important in the sense that we can also leverage the fact that we are a kind of interdisciplinary community. Yeah. To be even deeper into somehow putting in perspective this research around fairness of AI system, which in the past has been somehow very interesting, but kind of self-referential. While we move into an ecosystem with the different laws, or proposals of new laws, Europe is especially active on this area. So I think by framing your work also from a legal and an ethical point of view, it would certainly be a plus.
Yeah, just as a point, I think that Professor Comandè will be part of my panel, as I asked him, and he seemed happy to join. So there will be, of course, room for this aspect as well.
Yeah, this is actually one of the main purposes for joining in a day like today. Okay, thanks. Any other suggestions or questions for Andrea? So if not, thank you, Andrea, very much. Nice presentation, and we move forward with Filippo Galli. Filippo is talking about federated learning and privacy. So yeah. Please go ahead.
Yeah, good morning, everyone. Filippo here, and just a second till I share my screen. Okay, so I'll be talking to you about the justifications and open problems in federated learning and differential privacy. Here's a brief outline of what we're going to talk about, and it's first a brief recap of why we need private data science. Then we'll delve into two of the techniques that I'm most interested in, which are differential privacy and federated learning. So training predictive models training predictive models on user data is a fundamental part of data analysis and machine learning. And in an effort to increase the predictive power and accuracy of convolutional neural networks, recurrent neural networks, and all the standard building blocks of modern machine learning, which have millions of parameters, user data is harvested and centralized to efficiently run computations. And as a consequence, many actors are involved in the process. Users may generate training data through interactions with their devices. Machine learning engineers handle training and deployment of the models. Analysts may use the trained model for support in decision making, and so on and so forth. Ideally, each actor would have the least possible interaction with sensitive data, and the company or research institution handling them would follow the principles of data minimization, transparency, and the right to erasure. But given the increasingly detailed and private nature of these electronic records, there is a growing concern among users regarding the use and abuse of their data for profiling, targeting, or just the mere poor handling that led, for instance, to the Cambridge Analytica scandals a few years ago. And privacy breaches can lead to very harmful consequences. Can lead to disclosure of sensitive information, which in turn can be used for fraudulent purposes like identification, discrimination of all sorts, blackmailing, and identity theft. And so we might be wondering, what are we trying to do exactly? So when training a machine learning model over user data, we are interested in discovering the underlying probability distribution, and much less in the individual data characterizing a specific user. Such behavior is rather to be avoided, as we know, in fact, that overfitting is an enemy of generalization, which is actually our goal in machine learning. And we are dealing then with the problem, with the paradox of learning nothing about the individual while learning something about the population, the underlying population. Then we find the goals of privacy preservation and machine learning in this sense are kind of overlapping. In fact, say that we are running an experiment to find out whether smoking causes cancer, lung cancer. The information regarding the correlation between the two is not private, while the information that Alice smokes is private, and it's also useless for the model to generalize. So in 1977, Dallenius expressed a desideratum for statistical databases that in the following years led to the basis for the definition of semantic security in the context of crypto systems. This desideratum is that access to a statistical database should not enable one to know something about an individual that wouldn't be possible to know without access to that database. This requirement is probably impossible to satisfy. We have, in fact, the Terry Gross example, which is well known in the community. Say that an adversary has additional information that Terry Gross is 2 centimeters shorter than the average Lithuanian woman. If the adversary queries a statistical database with the average height per country and gender, they will find out how tall is Terry Gross. So the adversary, thanks to side information, has obtained private information about Terry Gross without her even being in the query database. So what typically happens is that different techniques try to compensate for this impossibility, typically relying on anonymization. And we have, for instance, k-anonymity, L-diversity, T-closeness, among others, all of which have computational problems, for instance. In fact, they are in general NP-hard, and every attribute, even after anonymization, can be a potential quasi-identifier. In general, as we saw, they're not robust against adversary side information anyway, which has led to multiple de-anonymization attacks. And we are ready now to introduce differential privacy, which is which follows from a relaxed version of the previous desideratum. Instead of requiring that access to the statistical database gives no additional information regarding an individual, we require that querying the database gives practically the same information whether the individual is included or not in the database. If the statistical queries on a database do not vary when one individual is added or removed, then we are querying distributional information and rejecting personal information instead. Differential privacy, in fact, provides a rigorous mathematical framework for the definition of privacy, for measuring the privacy leakage, and to enable differentially private queries with probable guarantees. So here we have a formal definition, which basically says that a query function K on any two databases, X and X prime, that differ in only one record, should provide results whose probability distributions cannot differ by more than a factor of e to the epsilon. This epsilon is then called the privacy leakage, and we will call such mechanism epsilon differentially private. We can take an example here, and a very extreme example, in fact, say that here we have two databases, X and X prime, and with data from a group of penguins, and one of the two databases has an additional record. We want to query the flipper length of a random penguin which it's under the probability distribution showed in the picture. The ratio between the solid and the dashed line will be e to the epsilon, and for some value of epsilon, and we can say the query is in fact epsilon differentially private. Clearly, if just the presence of an additional record changes the distribution by that much, this epsilon value, this privacy leakage, will be pretty big. And for those interested in information theory, we can draw a parallel here with information theoretic quantities and see differential privacy as a bound on the pointwise Kullback-Leibler divergence of the two probability density functions, or more appropriately is the alpha divergence when alpha goes to infinity. And one could wonder how would this apply in case of a deterministic function, and it turns out the differential privacy, as I mentioned earlier, also offers ways to sanitize a query function and make it differentially private by adding random noise carefully tuned on the query function sensitivity. Standard differential privacy with the above definition as a set, with that definition, there are a set of use cases that are excluded because it relies on the definition of databases as collections of items. A generalization of differential privacy is called D-privacy, which allows X and X prime to be any points in a space equipped with a metric D. This opens new scenarios to the application of differential privacy in many different domains, where X and X prime could be, for instance, graphs, geolocations, or single samples in a continual learning scenario. And regarding this point, I'm also happy to say that in the past weeks, I managed to get in touch with Professor Palamidesi, which suggested this generalization. And we are working to have me visit her in her research group in Paris as soon as we can make it possible. And since we are introduced the first technique, we can move on to federated learning, which is another complementary approach to the problem of statistical learning on a population while learning nothing about the individual. It is a paradigm for private distributed computing, where a set of clients collaboratively train a machine learning model under the orchestration of a central server, and any node is allowed to have access only on their own raw data. The raw training data is never centralized. Instead, the orchestrator collects directly the statistics from the participating clients on their local datasets. These statistics are used in rounds of training in order to update the global model. Although it is a general framework in the context of gradient-based optimization for neural networks, we have this algorithm called federated averaging, where we have the orchestrator sends the global model to the nodes, and then in parallel, each node performs a number of gradient descent steps over their own private local data. Then the local nodes send the local updates back to the orchestrator, which averages them and updates the global model. And this process is repeated until convergence. As I mentioned earlier, federated learning and differential privacy can be complementary approaches, And if we are training with a federated learning scheme, we can apply differentially private mechanisms in order to provide further privacy guarantees. In case of gradient-based learning, the query function we were mentioning when talking about differential privacy is a computation of the local gradient. So we see in the picture above here the local updates of 4 nodes for their parameters, which we'll call A and B. And before sending each local update to the orchestrator, the updates are perturbed with zero mean noise in red here, providing plausible deniability to the nodes, and instead providing accurate estimates of the updates once they are averaged by the orchestrator, again for the fact that we are adding zero mean noise. Federated learning is a rather novel technique for training machine learning models. In fact, the first paper appeared in 2017. And there are still many open problems. For instance, even securing communications with a server in an efficient way is one of them, considering that often computations in this setting are run on low power devices like a smartphone. And 2 other problems which I'm highlighting here are convergence and application of local differential privacy. In fact, some of you may have noticed that a core assumption of stochastic gradient descent is not respected in this framework. In general, in fact, the local data sets are not independent and identically distributed, and the local updates refer each to a different underlying probability density function. So convergence can be either slow or not happen at all, sometimes even without the additional noise of differential privacy. I should underline, in fact, that shuffling among nodes is forbidden if we want to preserve privacy, of course. And improving on the convergence speed and the actual convergence values of the loss function is one of the most active areas of research in federated learning in the community, being the most prominent open problem. And another assumption that may or may not hold is that we as users can trust a third party to apply the noise required by differential privacy. If that is not the case, the users may want to rely on local differential privacy and add the necessary noise themselves on not on the query function, to which they may not have access to, but directly on their data. The problem is that methods for local differential privacy are not trivial. And for instance, adding random noise to an image does very little to hide private data, for instance. Additionally, it's been shown how, especially in the healthcare sector, local perturbations tend to considerably undermine the accuracy of machine learning models for the tails of the distributions. Which tend to be where data of minorities lie, adding a further trade-off between privacy and fairness on top of that already that we have to deal with, which is the trade-off between privacy and utility. So with this, I'm mostly done with my presentation. I just want to add that my current supervisor is Tommaso Cucinotta, but I'm still putting together the panel. So if I sparked some interest in any of you, please reach out and let's discuss.
Filippo, this is
Thank you, Filippo. Yes, please, Giovanni, go ahead.
Yeah, I'm just a quick point, because from what I saw, it's intriguing and very interesting what you are trying to do, because at least Google is claiming that all its federated learning, it's fully preserving privacy, which is not entirely clear. Just a very small point here is the privacy preserving and the federated learning are basically, from your presentation, if I understood correctly, are largely relying on the trust we have in the intermediaries, basically. Otherwise, you have to lose just to pollute somehow the data yourself and to dilute them. So I would just suggest to take into account, as Dino was suggesting before, the proposed Data Governance Act, where basically all the infrastructure, the legal component for intermediary, trustworthy intermediary, especially for using personal data, it's forecast. And because that could be a key element in tying together the federated learning part and the differential privacy one. So just in case, send me an email and I can give you more details and hints. Right?
Thank you very much. Yes.
You're welcome.
Yes, this is a good point. I have another, Filippo, a very nice presentation. I like the project, of course. One aspect that I would also suggest you to take into account is that differential privacy has been widely studied, but also from a practical case, sometimes also somewhat criticized for certain application areas, because in a sense too restrictive, too let's say destructive on the value of data, that in a sense may confine the applicability to a very specific situation. I think that's something that tries to tackle these aspects, or at least somehow focus on what kind of analytical processes can be enabled by the kind of federated learning, privacy preserving framework you are proposing. I think it would be important now to motivate the fact that certain problems, not all problems, but certain analytical problems can be tackled in this way, because as such you would somehow also be resilient to the criticism that this is a kind of theoretical construction with little impact, which I don't think is the case, but it's important to somehow frame it application-wise, and also, as Giovanni was saying before, also from the point of view of what kind of, let's say, governance issues can be tackled in this area. I don't know whether this makes sense.
Yeah, absolutely. Of course, different problems require different solutions in general. And sure, for instance, if we have federated learning and we want to apply differential privacy on top of that with a couple nodes, that's a problem, because even if we add this noise and we average it out, we will hardly have a zero mean noise at the end. So I can see where this is very beneficial. For instance, in the case of Gboard, the Google keyboard for Android, they're relying on noise added to potentially millions of devices and data. So averaging out the noise there is a lot easier than in smaller scenarios. Yeah,
this is certainly a good point, because I think that especially in the past, differential privacy has been oversold for a kind of, panacea for all kind of problems, but this is not the case. Then this can backfire into. But I see you're perfectly, let's say, aware of this. Any other comments for Filippo?
Yes, sorry, if I may. I wanted to ask to Filippo if you had any specific applications exactly, or data sets in mind, such as healthcare data, or what type of data are you thinking to test your algorithms, or if you have any in mind, any applications?
Yeah, so I would rather stay as general as possible, but at the same time, I see that some applications require a more urgent study, let's say. And I think graphs is a data type that would benefit from the advances in differential privacy, especially when we are seeing with the generalizations of deep privacy that we saw earlier. It generalizes differential privacy to any universe of secrets. If this universe of secrets is composed by nodes in a graph, then we can apply differential privacy. And so, yeah, I think for some types of data and data structures, differential privacy is being tried, at least in the academia. and some others have been overlooked for a while, and I think it's a good chance to try it out on these funky kinds of data like graphs, or even in weird in other settings like in the continual learning scenarios where we again don't have the two databases to which we can find the Hamming distance between the two, but we can extend the definition as again with deep privacy and see each single point as each single sample as a point in this new universe of secrets.
So yes, thank you very much, Filippo. Certainly true that some concrete case study will benefit, certainly will make your project even stronger. I think we are in only 5 minutes, 6 minutes late, not too bad. So I would say we now stretch our legs and arms and get a coffee, and we get back in 15 minutes sharp. So 10:50, we convene back here, and it will be then Francesco Spinnato, the first speaker. So talk to you in 15 minutes. Thank you all. Hello, everybody. Welcome back to the PhD Day. Can you hear me?
Yes.
You're live?
Yes.
Okay, very nice. We have now next in line Francesco Spinnato. Francesco, yeah, is talking about explainable AI for sequential data. So
exactly,
it is your turn. Go ahead, Francesco.
Yeah, let me share my screen if I can. 1 second. Sorry. Can you see it now?
Yes. Yes.
Okay.
Perfectly.
So good morning, everyone. My name is Francesco Spinnato, and the main focus of my research is interpretability for sequential data. And the temporary title of my project is Explanation Methods for Sequential Data Models. And I'll be very quick with my introduction, because I think that we all know that interpretability is becoming more and more important. And the main reason is that machine learning models are very accurate, but they are in a sense opaque, in the sense that they are difficult to understand from a human standpoint. And so they are often called black box models. And the interpretability is widely studied for certain kinds of data. So for example, tabular data, images, and partially for text. But there is a lack of literature for interpretability approaches that can be used to explain machine learning models that work on sequential data. And with sequential data, I mean any kind of data where the order matters. And this is a big problem, because sequential data is often used in many critical situations where the explanation part of a black box becomes extremely important. You can think of, for example, about the healthcare domain, where the majority of body signals are in the form of time series, or you can think of early warning systems that use seismic waves in order to predict the intensity of an earthquake, and the list, of course, could go on. And so, given this lack of, given this gap in the literature, my main goal for this project is to study, design, and develop interpretability approaches in order to explain black boxes that work on sequential data. And I want to analyze this problem from 3 points of view. First of all, the point of view of the input, and that means that I want to be able to explain black boxes having different kinds of sequential data input. For example, univariate and multivariate time series, discrete sequences, item set sequences, and so on. Then I want to be able to explain black boxes having different kinds of outputs. For example, labels for classification problems, continuous values for regression and forecasting models. And these latest two, so regression and forecasting, are extremely important for sequential data. So I really want to tackle this problem. And finally, I want to be able to be flexible in the kind of explanation that I can output. Because certain problems could require different kinds of explanation. For example, a feature importance based one, or decision rules, and so on. And my final goal is to have a modular framework whose parts can be changed depending on the specific problem. So the specific input, output, and type of explanation required. And I started working at this problem for my master thesis, where I developed LASTS, that is a local agnostic subsequence-based time series explainer. And this is a framework that can be used to explain the decisions of black boxes, in particular classifiers, that work on univariate time series data. So by following the schema that I showed you earlier, we have as input, we have univariate time series. As output, we have labels, so a classification problem. And as explanation, as we will see, we have decision rules. And last year, we published a first version of this framework. And this year, we updated it. And I'll talk about the latest version, because from our tests, is also the fastest and in general, the best one. So LASTS is an agnostic model, and that means that it can be applied to any black box without basically making any assumption. It is local, and that means that it can be used to explain the decision for a single instance and not the entire black box. And finally, the explanations are subsequence based, and that means that they are based on a subset of observations of the time series. And this kind of explanation is quite interpretable from a human standpoint. But I think that the best thing is to start with an example, and I think it will be clearer. And let's say that we have a data set that contains time series having 3 different shapes, and so they belong to 3 different classes. So we have cylinders, we have bells, and we have funnels. And then we have a time series X and a black box that correctly classifies this instance X as funnel. And our question is why? Why the black box classifies this specific instance in this way? And what's the reason behind this decision? And the answers that LASTS gives are of 2 kinds. The first kind, you can see it here on the top row on of the answers, and it's a more visual and intuitive part, and it's composed by exemplar and counter-exemplar instances. For example, here you can see in green exemplars, and these are instances similar to the instance we are trying to explain, and they have the same class. And so they are all funnels, and they are a sort of prototype of our time series X. Instead, here on the top right, we have counter-exemplars and in red, and these are instances similar to X, but they have a different class. And so they show us how the decision of the black box changes depending on the shape of the time series. And so you can see here in this very simple toy example, if this right part of the time series becomes higher, as here, then the class tends to change from funnel to another class. Okay, then we have the second part of the explanation that is rule-based. And on the bottom left, we have the factor rule that explains to us the decision of the black box in terms of logical conditions that are based on time series subsequences. So in this very simple case, if this subsequence here, 245, is contained inside the time series, then the class is funnel. Finally, we have the counterfactual rule that is the minimal variation in the factor rule that results in a different classification. So in this case, if the subsequence 245 is not contained in the time series, then the class is not funnel. And so this is the final explanation of LASTS. And now I'll talk about briefly and at a very high level on how this framework works and how its parts works. And I talk about parts because LASTS is a modular framework. And so it's composed by various modules, and they all have their particular purpose. And probably the most important module of this framework is the so-called autoencoder. That is a neural network composed by an encoder and a decoder, and they are trained in order to compress and reconstruct their input instances as well as possible. So in this case, for this problem, the input instances are, of course, unidivided time series. And so we can pass our time series X to the encoder part of the autoencoder that compresses it, that encodes it in a so-called latent representation. And this representation here is far easier to handle with respect to the original time series. As you can see here, in fact, this time series X is very long. It has 128 observations, and it's compressed in a bidimensional vector, so only 2 values. And we call this vector Z. So Z is the compressed version of X. And being bidimensional in this toy example, we can also visualize it in a Cartesian plane, as you can see here. Then we have the second part, and this is called the neighborhood generation. And in this phase, our purpose is to find the decision boundary of the black box locally. And this is the portion of space in which the decision of the black box changes. And in order to do that, we perform a search, and we search for the closest instance to Z that has a different class. So we are searching for the closest counterexemplar of Z. And in practice, it's the closest instance to this point here that is not a funnel anymore. And there are many ways to perform this search. And in the latest submission of lasts, we tested many. But for now, let's say that we find this instance, and by definition, this instance will be very close to the decision boundary. And so by sampling a neighborhood of instances here around this instance, we will find both exemplars, so that you can see here in green, and these are all funnels, and counterexemplars that are instances that are not funnel. Then, once we find these instances in the latent space, we can decompress them with the decoder, and they return to a time series representation. And as you can see, this is the first part of the explanation that I showed you earlier. Okay, and finally, in order to obtain rules, we need a surrogate that is a machine learning model that is trained in order to imitate the decision of the black box on this local and simplified decision boundary that we just generated. But we don't train directly the surrogate on this time series. We first extract some interpretable features from them. In particular, we extract the discriminative subsequences. And on this new representation, we train as a surrogate a decision tree, because from it is extremely easy to extract the factual and the counterfactual rule by following the paths from the root to the leaves of the tree. And so this is the final explanation of lasts. And I think that I explain it all to you. And the interesting part is that last is modular. So we can also test different components for each module. And maybe I need to be quicker, but I'll talk about a little bit about various alternatives that I'm testing. For example, for the autoencoder, right now I am testing variational autoencoders because they ensure that the latent features are normally distributed, and this property greatly simplifies the neighborhood generation part of the framework. And then I'm also testing with other autoencoders, and I'm also testing on integrating some information of the black box inside the training process of the autoencoder. Then for the neighborhood generation module, instead, we tested many alternatives in the latest submission that we did. And the first thing that we tried was a genetic algorithm that, for those who know, is the same used inside LoRe. That is an interpretability approach for tabular data. And but now that we are sure that the features in the latent space are normally distributed, we can also use random approaches that from our tests are also very, very good and also much, much faster. And finally, we can also test with different surrogates, of course. For now, we only extracted subsequences as interpretable features. We tested many kinds of extraction. And instead, for the classification model, given that we want rules, for now, we only tested trees. But of course, we could test with other interpretable or linear models. We are also generalizing this framework to multivariate time series, and this is quite easy because basically the framework is the same. The autoencoder is very similar. The neighborhood generation is basically the same because it happens inside the latent space, and so it's not influenced by the shape of the input. And the only thing that really changes is the surrogate, because we need an interpretable model that can work with multivariate data, and there aren't many in the literature. And what we did for now was a naive approach to extract from each signal of the multivariate time series the subsequences, and then train a unique tree on this big data set with all the subsequences. And this is a very simple approach, but seems to work pretty well. And so here you have an example for a multivariate funnel. So you can see here, this is a unique funnel with 3 signals. And here you can see exemplars, counterexemplar, factual, and counterfactual rule. Finally, of course, there are a lot of things to do. And the first thing that I would like to do is to test this framework on more real-world datasets. For now, we tested only on 4 very simple datasets. And I really would like to test on audio data, because I think that it would be very interesting from an interpretability standpoint to be able to hear an explanation. But the main problem that I'm facing is that audio data is basically a very, very long time series. And so it's very hard to encode and decode with the autoencoders. And then there is the problem of regression and forecasting model. And this is a very big problem, because probably for now, I only tackled the classification problem. And so these new models will probably require a new approach, or maybe generalizing the current framework in which many concepts are deeply label based. And finally, once my main goal is, once I have this framework ready for univariate and multivariate data for classification, regression, and forecasting models, my main goal is to try to explain different kinds of sequential data, like, for example, discrete sequences like text or MIDI files or item set sequences, and so on. But this is an open problem. And that's it. Thank you very much.
Thank you very much, Francesco. Are there questions from the audience?
Okay.
Can you hear me?
Yeah.
Hi, Francesco. Thanks for the presentation. I'm not too much into these explainability issues, but I just wanted to ask you just a quick question about what is the 245 number you were showing in one of the first?
Yeah. That's
just clarify a little bit the technical aspects, if you don't mind. Maybe it's just me not knowing too much there, not be too.
Oh, yeah, you're right. That's just because we extract a lot of subsequences. So that's just the number that the number of the subsequence that the decision tree is using.
Okay.
So it's just the number of the feature is not nothing special.
Okay, great. Another question, actually, I was about to ask you, but you prevented me because you said something at the very end. So about multivariate data, as you might, yeah, this is Google telling me to clarify better. I mean, it was also posting questions, but the assistant kicking in just without any possible meaning, any possible sense. So my question was about with this multivariate data. We have quite a lot of this, or at least we are analyzing a lot of this multivariate data in a context where there is really a huge volume of this data coming, which is that data center monitoring and control, and operation. So in that context, you may have really imagine, one single value kicking in every 5 minutes, then multiplied by 200 values per virtual machine, multiplied by 40 to 100 virtual machines per physical host, times thousands and thousands of, even tens of thousands or even more physical hosts per data center, and you make the maths, the calculations. So if we wanted to make something AI enabled, and we try to make, of course, classification is a big something that gives value a lot. Knowing that some patterns are spread across the various functions and places are similar is something that brings a great value. Yeah, but also forecasting is something that is very, very interesting. And especially forecasting behaviors and also trying to understand whether behavior will fall or is about to fall within, I don't know, an erroneous modus of operation. We fall within a particularly bad class of behavior, stuff like that. So in this context, I mean, being able to explain why your AI model is, is pointing you this, is giving you this output is something that would be really useful. Very often we face with problems like this, with operators from, in our case, with the network operator, and sometimes they are very puzzled. I mean, people working in the domain, they don't figure out, I mean, why do we get this output? It would be really be adding a great value to be able to explain why it is why, and to accompany the model output with this information. So just a comment on the relevance of the research, which I find really, really interesting. Even in time series analysis, as I see, it's probably there's been a lot more being done in this field with computer vision, right?
Yeah.
But with time series, probably we need a lot of work.
Thank you, Tommaso. Thanks, Francesco, for the nice presentation. Are there any other comments or questions for Francesco?
I have a comment, if I can.
Please.
Thank you, Francesco, for the presentation. Your work is really interesting. I worked a little bit with sequential data, explainability on sequential data. And one thing that I find really interesting is the interpretability of the final explanation. Because if you can go to the slide where you provide the explanation, I see that you stopped sharing the screen. However, I would ask you to elaborate a little bit more on the explanation that you provide. And if you think that this explanation is interpretable, so who's the user, the final end user of your explanation? Is this interpretable for the end user? Because I think sometimes we forget that explanations are not only for computer scientists, but also for other kind of users. And so I wanted you to elaborate a little bit more on what does this explanation mean. So how can we read this kind of explanations?
Yeah, there is a lot to do in order to make explanation really simple and understandable from the point of view of anyone. And for now, this is more for machine learning users, of course, but this is the first step. And for now, how I do interpret these explanation is that, for example, for the rules, here you can see that the black box model is looking at this angle here of the time series. And so it is saying to us that if a time series contains this angle here, then the class is more likely to be a funnel. That's the main thing. Then you have also the counterfactual rule that it's like the minimal variation that results in a different decision of the black box, and then I think that this first part here of the explanation, it's quite interesting, but it really needs some work, because maybe a more intuitive and visual part would be better understandable from maybe a common user. But yeah, there is
because when you use autoencoders, then you lose a little bit of the interpretability. And so it might be interesting maybe for you also to think about some interpretable representation of the raw data, where you can perturb your data on the, you know, so you could maybe, because autoencoders are really efficient, of course, but at the same time, you lose a lot of the interpretability of the features. So you don't have any control on you kind of the output that you actually have from these autoencoders. So another thing that you might consider to do, if I think it would be interesting to see, is actually to look at some interpretable, you know, perturbation in a way. So you have the full control on the interpretability of the process.
Okay, thank you.
Thanks. I think you got, Francesco, some hints. In the end, however, of course, where the explainable AI research is certainly aiming at is somehow not only developing methods that, like you very nicely showed us, but also to find ways of validating that the provided explanation are useful for the intended class of users that we have in mind. And this is certainly a good point. I'm pretty sure you're aware of the challenge. Okay, so thanks a lot. Nice presentation. We can move forward. And the next is Jose Manuel Alvarez. Jose is one of our two PhD students from the first year now from the twin Marie Curie Action Project, No Bias, led by Salvatore Ruggeri. And Jose is talking about counterfactual reasoning for ranking. So, Jose,
can you see my my screen and hear me?
Yes, and we can hear you well.
I'm trying to get into full screen mode. There we go. Yes. Good morning, everybody. Well, the title is a bit different from the one I had in the abstract, but it's the same in spirit. So my name is Jose Alvarez, and today I'm going to be talking about my research ideas on bias detection in data for automated screening processes, which are also ranking algorithms, via causal and signaling models. And as Dino mentioned, I'm also part of the No Bias ITN, and as well as the KDD lab, and I'm under Professor Ruggeri's supervision. So today's agenda, I'm gonna present a bit automated screening processes, then a bit of bias and the sources under this context, revisiting the sources through a motivating example, and then wrapping it up with the PhD project or the idea I have in mind, which a brief conclusion I can say now. It's just I would like to then extend the use of counterfactual reasoning or causal models for automated decision making with some notions of signaling models from information economics. So automated screening processes, I think we're all a bit aware of it. And, you know, it's a matching process between a screener and a set of individuals or applicants in an applicant pool. And it's a three-step process, usually: search, sort, and filter. Search, where there's a call for applications and people who are interested search for this application and apply. You build an application pool, and then this application pool is sorted by the screener using some variable of interest. And then you filter out those candidates that you don't like, and you take the top K that you do. So examples are job applications, college admissions. Even some of the dating apps could be rephrased as a matching/ranking process. And nowadays, you know, with the technology, we can replace a screener with a ranking algorithm that has some properties that are a bit more appealing, at least in theory, such as, you know, consistent decision making. And we do this by training the algorithm on some historical data of previous automated non-automated screening processes usually. But we still face the old concern that, say, we had in the 60s when we were looking also at screening processes. And that's what's the role of gender, race, or what legal scholars would say, protected attributes in this now automated process. So a bit of a meme to summarize what might be the issue with this. And it's essentially that we're training it on biased humans. So what happens is that ideally, we would like that the protected attribute A plays no role in this the screening process or the final ranking, if you will. And only the feature of interest X matters, meaning that the feature of interest for the screener, such as the candidate's quality or years of experience, and so on, it's the only thing that determines the outcome of this decision-making process. But as we all know, and I think most of the people in this group, the ranking algorithms are not immune to human biases, and they can then result in discriminatory and unfair practices towards, say, even amplifying them. One example was Amazon's 2008 hiring algorithm, which was found to be biased against women, and then they had to retrack and take it from production, actually. And we have a bit of this worrisome machine learning pipeline where you kind of have a bit of bias in, bias out, what they say is a bias laundering. And because the training data is made by and from humans. So I like to see this a bit like an inherent bias property that it's on training data, it's that it has this human bias element. So a bit overall with bias, because I think it's important to just say what we mean. I mean, the way I like to see bias is just an acceptable preference towards, say, according to societal standards, right? What do I mean by this is, for example, the Amazon hiring problem. If this probably came out in the 60s, maybe we wouldn't have made so much headlines, no? And it's a bit bias. It's not it's not timeless. It's not constant, you know, it's a changing variable itself of what we mean by something that being acceptable or not towards a protected group. And the issue with bias, it's often unwanted, unconscious, and sometimes apparent only in hindsight. Or sometimes even worse, we can take it as givens rather than treat them as historical processes. So what I like to consider like a new textbook example is the case for safety standards in cars and bias towards female passengers. So they actually found that when the survival rates are also like the injury rates between female and male passengers in car accidents were quite different. They did some digging. They found out that the crash dummies used for testing the safety features of cars were actually only made under male specifications. So you never really tested what might happen for a female passenger and never readjusted the car's composition. So of course, this was not on purpose. This was a bit unconscious, and it only became apparent, you could say, too late. And maybe it was seen also as a given because, you know, that's the way we do stuff, and nobody really questioned the consequences of such practices. So this is a trickiness behind bias. Now, sources of biases, I subscribe to this view that, you know, you have a trainer bias and a screener bias, and this says that, you know, there's a lot of bias you get from training the algorithm, and there's another type of biases that you get just by deploying it and let it go wild. And so I'm focusing here on more trainer bias, which includes the biases coming from the data for the automated screening process, and their potential sources. You would have like a representation of A, mislabeled data, data construction. So both, for example, the Amazon hiring case and the car fatality case, or a bit of like a representation of female data subjects in the sample. So bias can be measured in the ranking context, usually through 3 approaches: exposure, probability, and recently counterfactual-based approaches. So exposures, it's more out of your 10 final candidates, how many of those are from A equals A star and A equals A dash, right? So then you would like to have a similar exposure. There are also approaches that look at the position in the final ranking. So who's in the first place and the second place. There's also a probability approach where you're just interested that the probability of one member of one group ending in the final ranking should be similar to the other ones on that feature space. And recently the counterfactual approach where we're interested in the what if the candidate was from one group instead of the other, say male or female. And then we would then compare the original ranking with the counterfactual ranking and see if they differ. But I'm interested a bit in revisiting these sources of bias, because I think what they sometimes miss is that the training data is human-made. And I mean, this is a bit trivial. Of course, it's human-made, but what I mean by human-made here is that this is the product of the exchange between an applicant and a screener, which are both human agents with agency, right? So treating the data subjects when you have the training data as data points sometimes denies them of the agency and overlooks aspects of bias formations. Why? Because the applicant, in a way, chooses the signal they decided to send, or chooses unconsciously, and the screener also chooses how to interpret it, sometimes also unconsciously. So under agency, I'm interested a bit in refocusing the exchange of the signals, which is what is the signal of interest, X. So these methods, the previous one, they take X more as a given, and I was wondering, could something more be said about it? So I'd like to motivate this with an example. I don't know if anybody's a Park and Recs fan, but this is a data science interview with where you have two remaining candidates, Ron and Leslie, and they're applying for a data science position. And the interview is indifferent between the two of them at this point because they're quite good. And they're both similar in the sense that they're both computer science graduates from University U. So let's consider two scenarios for the interviewer. One, the interviewer knows how rare it is to have a female graduate from this university in computer science and picks Leslie. And a second scenario, the interviewer goes over the CV again and now focuses specifically on programming languages and says, okay, whoever has the best skills, that's it. And then, you know, Ron puts advanced in Python, intermediate in PySpark, and Leslie intermediate in Python. So they're from the same university, but maybe Ron had a bit more guidance or better projects and got a bit more advanced. But then the candidate remembers that there's some evidence, the interview remembers there's some evidence that men tend to overestimate their skills during interviews while women tend to underestimate theirs. So should the interviewer still pick Leslie over Ron or pick Ron over Leslie? So in a way, these are signaling examples, right? Because both instances, it's kind of readjusting X based on some domain knowledge. So in the first one, Leslie's signal becomes more impressive to the interviewer, given that the interviewer knows that maybe this University U is very tough for female candidates to succeed. So the signal has a bit more meaning because you could argue that Leslie pay a higher cost to saying the same signal as Ron. And in the scenario two, it's cheaper for Ron to lie than for Leslie to tell the truth about their skills. Or similarly, it's cheaper for Ron to lie than for Leslie to lie as well, because she's not advanced Python, but she could lie as well, but she doesn't. So they're both there's a mismatch between their signals and their abilities. So to me, this has also implications beyond pairwise comparisons, right? Like, because is this the case for all male and female candidates in the rest of the application pool? So if so, should the interviewer reconsider the entire ranking when he or she considers this approach? So I see it as a potential source of bias because you could have misleading signals. And then such a type of exchanges in a non-automated setting are exactly what they add up to the training data set that you can use for the machine learning algorithm or the ranking algorithm. And then the ranking algorithm will just take X as a signal, so it doesn't have to consider the agency and the interaction. So for my PhD project, I'm interested in formalizing the signal readjustments for tackling bias. You know, for example, on applications, we might be interested in finding a way of reweighting X based on a certain signal setting and the bias the data before feeding it to the algorithm. And I'm specifically interested in extending the counterfactual reasoning from the structural causal models, because I think counterfactuals offer a very unique opportunity in the setting of rankings, because the what-ifs are positional. So it kind of gives also an order, and it's a bit more clear on what we're trying to say and what we mean with the what-if candidate. You know, what if candidate 10th would have been in candidate 9? So what would candidate 10 have done differently to be in the 9th position? But at the same time, they're a bit under attack regarding their treatment of A, because it's a bit counterfactuals, or this idea of alternative realities or parallel worlds where we can intervene on one variable and we would have been on this different parallel path. It's also a bit in question that not all candidates, given their characteristics, would have even had access to such opportunities to even be in that position, to be parallel to the current world. You know? So in other words, A determines a bit the signal that you can send. So not all signals are available to all candidates. Right, so that and I think there's a need more on making the counterfactual reasoning more robust to better reweight X. And I think one way of doing that could be to explicitly model this exchange between the candidate screenering as a signaling model, which also would allow us to treat A more, well, now it's a bit more in the news, but as a social construct, or a bit more like a thicker concept. So the project would would extend the causal modeling framework a bit more by bringing two aspects, signaling models and social constructs. So signaling models, to give it a bit more of a formal definition, it's just a game where information is exchanged between two parties or two agents, but here the information is asymmetric. Usually in screening processes, for example, only the candidate knows whether she is a good or bad future employee. And then the screener has to guess based on the signal they send and based on previous success stories of the screener himself, you know, so some generalizations, based whether that candidate will make a good fit. You know? Because at the end of the day, you hire somebody and maybe you have to wait 6 months to realize if they're good or not at what they do. And then that it's very expensive to fire them. So for example, Leslie and Ron, for this data science interview, had to prepare a CV, had to interact with the interviewer and so on, but the CV itself, what you put and don't put in the CV might be a way of signaling and might say a bit of what the candidate's trying to say, similar to what the interview wants the candidate to reveal. And then social contracts, so it's taking the protected attribute a bit beyond the label. No? So not say race, not as a phenotype or an observed or a perceived race, but it's also like, what do we mean when we talk about, say, a female candidate behaving a certain way in an interview? So there's a lot of views on this from the social sciences, especially on this type of behavior. So what I see here is that the way the agents send or interpret these signals might depend on social expectations around how a member of that group should behave. So going back to that example is, why would Leslie underestimate her skills in this interview setting? You know, does she, for example, is expected to behave, say, modestly in the interview? And then the idea would be to build then a causal modeling framework that could frame such types of signaling games and build more on a complex notion of A that would allow to readjust the signal for X. So for example, in the counterfactual setting, under this setting, would Leslie actually be Ron's counterfactual, or would it be somebody else? Because maybe her signal is a bit better. So that's more or less the idea. And then, so moving forward, then I will have, as part of the no bias, we'll have a secondment after summer with Generali. So I'm hoping to work with some data on screening processes from their side. And then next year we'll have a secondment at KU Leuven with Professor Bettina Parent on bias in data representation. And throughout the next year, my plan is to explore deeper the links between machine learning and MD as a mechanism design, which is the field that covers signaling games. And we'll have with a focus on social constructs. And the idea would be to then extend the social causal modeling framework and of course apply it to some real / simulated screening data. So thank you for your time. I'm open to questions.
Thank you, Jose. Nice presentation. I don't know if there are questions or comments. One that I have actually is, I believe that from your presentation, actually your mechanism design approach, what you're actually designing is not only the algorithmic part, let's say, of the, for instance, the ranking procedure, no, of a admission or recruiting commission. We actually do something more than that. You are actually designing how the recruiting board works and what is the interaction between. I believe somebody has an open mic in the background. Okay, thank you. So is that correct? So is that correct that you're not simply designing, let's say, the AI very broadly system taking part of say a recruitment session, but you're actually trying to design the overall process in such a way that is more resilient with respect to bias, and you put the let's say into the system the ability of being more able to recognize and somehow bias and de-bias the ranking. Is that correct, or did I miss?
No, that's correct. I actually, because for example, the initial idea, well, it's still an idea, but it was the bias detection data for and from automated decision processes. But the focus, at least on these slides, is on data for. So I see it more even before reaching the algorithm. But it's recognizing that maybe within the data you have for training, there's some sort of hidden agency that has not been considered, that then when we feed it into the algorithm, maybe we could extend the signaling model as well within the algorithm, but maybe it might be a bit tricky because you might have to then alternate between solving these signaling models and also optimizing the classifier, because these signaling models themselves can have, say, multiple equilibria, and so they could get very nasty as well, depending on the framework. So what I was seeing is more also from the angle of domain-specific knowledge, because I think it's very common, at least I had this in I guess a personal experience when I would do interviews for candidates in data science, about when you would read the CVs and then you would interpret the CVs, but then you would also know that it was very uncommon from one university to have that type of candidate, and you would say, that's very impressive. But I think that subconsciously, when we try to interpret that, is we do this signaling reweighting, because the signals, maybe they're the same, the CVs are very similar, but because you have some background knowledge that then you incorporate, and then you do your own reweighting in the decision making, and that's the human doing it. And I think that could be formalized, and at that point of the data formation, and then maybe as an end goal, I was seeing that you would have the original data set and say, and maybe you could do some sort of ranking algorithm just to show how would that data fed to some algorithm look like. But then you would also readjust the data based on, okay, I'm assuming this signal interaction is taking place, where I assume this of this candidate and that of those other candidates. How would my data look like then under this construction? And then maybe how would that result in my final ranking? But I don't think it's exclusive. Like, I think we could use this for the pre-processing steps, but I don't see why not in the in-processing.
But in a sense, what I see also interesting is the fact that you could frame this into, let's say, the human in the loop framework of human-centric AI. So in a sense, that would bring, I believe, an interesting light on your approach. But I think you're aware of this. Any other suggestions?
Yeah. This is Giovanni Conde. If I may, Jose, it's really, really, really ambitious what you are presenting, and really, really interesting. We'll discuss later today, but just one minor but probably problematic point, because the signaling mechanism you are describing seems to me it's highly dependent on the logic even of the algorithm you want to develop. Because the readjusting phase, it's a loop of a circularity of information, of the flow of information coming from the different players. So have you considered how to incorporate the risks of just trying to chase the tail, basically, having a loop on the one end, and the second, how would you incorporate in the theory you are developing, basically, the fact that the development of the algorithm depends from the logic that algorithm is developing on the one end, and the fact that without knowing what would be the algorithm, the signaling cannot be readjusted.
It's a good point. I mean, I have given thought, because it's indeed, I'm not claiming that, and I don't think if you could readjust X ideally, you then fix bias, no? Because then the way maybe the algorithm, even if X is truthful, the way the algorithm optimizes for X and then connects it to other variables in the data set, you're still a bit on the wrong side. So what I was, the way I was seeing is more maybe adding to that, right? So, okay, given those other considerations, maybe we could add on something more on X, but yeah, I guess the short answer is very tricky on the loop, because I understand what you mean, that then if I then readjust and my algorithm still does bias and then that's refed into future data, then, you know, I'm not really doing much. That's why I also wanted to isolate at least the problem set, as to say, well, I'm only focusing on non-automated data that would come from purely human interaction. So historical data, maybe from the last 10 years. And then just see on that specific case. But then I think future extensions, one could be then maybe making this more interactive, no? Not only on the loop with the algorithm, but say also maybe with the final human decision maker, where maybe the ranking is final, but then the human has to pick, say, the top 5 of that ranking.
Sorry for, I hate to be the one who cuts the discussion, but please remember that this is the beginning of a discussion, right? In a sense that it's very nice that we have a lot of interest about what are the research projects of our fantastic PhD students. The key point is try to make a very, let's say, interested and committed panels that can assist them during their research. This is actually the main purpose for today's meeting. It is going to be recorded, so it's also visible to the members that are not with us today, for instance, for time zone constraints. I appreciate, by the way, very much that Giovanni, who's actually located in Canada right now, is listening in the middle of the night, of Canadian night. But yes, this is something that continues in the next weeks to create very well, let's say, committed and interested panels for the students. We can now proceed. Thank you, Jose, very much. Very nice presentation. We can proceed further with now Mila Andreani. We are running something like 12 minutes late, but of course, Mila has canonical 20 minutes. We'll simply make the next break 10 minutes shorter. Please, Mila, it's your turn. Tila is talking about forecasting in high frequency data or mixed frequency data.
Okay, just a moment, because I have to allow my screen. I just have to leave the presentation for a few seconds. Sorry, I'll be right back.
As Mila gets ready with the presentation, I really would like somehow to have from the board members their availability to be part of the panels of certain, with respect to which are particularly interested, so that we can, together with Joanna, and we can finalize a proposal for the board. Of course, for supervisors and the panel. Please, Mila, go ahead. We see your slides.
Sorry for the interruption. Okay, so today I will talk about the main advances in my PhD project. In particular, we'll talk about forecasting quantiles with random forests and mixed frequency data. In particular, we show some applications in the financial field, especially regarding the computation of value at risk. So I will starting by introducing value at risk, and then I will talk about the two main models that I've developed in the last few months. So in particular, the financial crisis happened in the last 2 decades have highlighted the role of value at risk as the first choice market risk measure, as prescribed by the Basel Committee. In particular, value at risk measures the maximum probable loss suffered by a portfolio or an asset, given a certain probability tau, which usually is set to be 1% or 5%, over a pre-specified time period, which usually is 1 day or 10 days. So in this sense, it's natural to express pilot risk as the quantile of a financial variable y. And under a statistical and methodological point of view, pilot risk can be evaluated by using quantile regression. But before talking about quantile regression, I will briefly talk about the main issues. Forecasting pilot risk has some challenges, mainly related to the presence of stylized facts in a financial time series distribution, such as updates or skewness, which violate statistical and econometric models, as well as the presence of complex relationships among financial and economic variables, and also the presence of mixed frequency data, which are related to variables sampled at different frequencies, which prevent the use of many potentially useful predictors in the computation of pilot risk in classical statistical models. So given the relevance of these issues in the forecasting of pilot risk, many contributions to the literature have developed models aimed at separately treating these challenges. So for instance, quantile regression has been extensively used in the financial field, given that it allows to model non-Gaussian data generating processes, such as the one generating financial data. But also machine learning algorithms are known for their ability to model complex and non-linear relationships among variables. Regarding the third issue, instead, it has been addressed in 2004 with the introduction of the mixed data sampling model, which allows to consider variables sampled at different frequencies in the same linear model. However, these approaches have never been merged together in the literature. So what I've tried to do in the last months was to develop, in particular, two models aimed at merging these models. In particular, I've developed the dynamic quantile regression forest, which allows to account for the evolution of quantiles over time, since one of the main features of financial time series is that the distribution changes over time. And also I've also developed the Midas quantile regression forest, which represents an extension of the random forest algorithm that allows to consider low frequency variable information in a quantile regression framework. So I will start by briefly introducing the dynamic quantile regression forest and by explaining what quantile regression is. So quantile regression is an extension of the linear regression that instead of estimating the expected value of a random variable allows to estimate the entire conditional distribution. And in particular, the parameters in the linear model, the beta parameters, are computed as solution of the minimization of a quantile loss function, which is an asymmetric loss function that allows to give a different weight to values that go above the computed quantile. In particular, as I said before, one of the main features of financial time series is that the distribution changes over time, and as a consequence, also the estimated quantile. So one of the most important contribution is represented in order to model this feature is the conditional autoregressive pilot risk, which directly models the quantile instead of the entire conditional distribution by expressing the quantile as a function of the lags of the returns and past values of the quantile itself. So given the relevance of the quantile regression technique in general in many fields, not only the financial one, also quantile regression has been also applied in the machine learning field, especially in 2006 with the introduction of the quantile regression forest, whose aim is not only to estimate the expected value, like random forests do, but also to estimate the entire conditional distribution by computing the quantile by exploiting the condition of quantile itself. In general, the quantile regression algorithm, it's based on the original random forest algorithm, whose aim is to minimize the sum of squared errors in each node in order to optimize the training of each tree. But in 2019, this approach has been further optimized for quantile regression purposes with the introduction of the generalized random forest algorithm, which allows to directly minimize the quantile loss function instead of the sum of squared errors in each node. So what I did was to extend in a dynamic framework these two models by developing the dynamic quantile regression forest. And in particular, I've developed this model in order to compete with traditional econometric models in terms of accuracy, computational effort, and interpretability. That, as already Francesco explained in his presentation, it's one of the main issues with in the machine learning field. So in particular, the quantile regression forest has been implemented by exploiting three principles. The first one, it's related to consider previous quantile predictions as additional covariate in the training set. So in this sense, we are in a autoregressive framework like the caveat presented in the previous slides. And to do so, I've exploited a recursive training and adaptive hyperparameters in order to adapt to a training set it's more complex as the iteration goes on. Regarding the empirical application, I've used my model in order to forecast the Standard & Poor's 500 index value at risk for both 1% and 5%. In particular, I've used the 14 covariates related to 4 of the main drivers of market risk that you can see in the slide. And here in the slide, you can see the results of the empirical application in terms of quantile loss and backtesting procedures. In particular, backtesting procedures are statistical tests used to evaluate the statistical adequacy of value at risk forecasts. So as you can see, the table I've reported the p-values of these tests, as well as the ratio between the quantile loss of my model and the quantile loss of the competitor models. And as you can see, for the percentage of this ratio, every percentage is below the threshold of 100%, meaning that my model delivers the smallest quantile loss. And in terms of p-values for the backtesting procedures, my model also delivers the other weight bar forecasts. In terms of execution time, my model is in the generalized random forest specification, it's faster than the quantile regression forest specification, as well as the traditional models used to compute dynamic quantiles, so the 4 specifications of the caveat. In terms of interpretability, also, I've exploited the relatively high interpretability of random forest, and this is also why I've decided to focus on these machine learning algorithm instead of others. So I've also computed the variable importance of the past quantile predictions in the training set. And as you can see with the blue bar is reported the variable importance that it's higher than 0, but also higher than other variables that are traditionally used to compute value at risk. So regarding instead the second model, the MIDAS quantile regression forest model, this model combines the mixed data sampling approach applied to quantile regression and the quantile regression forest algorithm. And this approach delivers two benefits to the computation of quantiles because it extends the MIDAS model to a nonlinear framework, and it also extends the applications of random forests since that it allows to consider mixed frequency data, which are not directly handled by the original random forest algorithm. In particular, the mixed data sampling model has been introduced in 2004. And in order to introduce it, I will denote the dependent variable as YIT. So there is a variable sample at time I of the tape period of the year that and with Z a low frequency variable. So for instance, in a value at risk setting, the dependent variable Y might be represented by a daily return, whereas Z might be a variable indicating the general state of the economy, which is observed at a lower frequency than the dependent one, such as the GDP or inflation. So given this notation, the MIDAS model is represented by a linear model where the covariate, it's the MIDAS component, that considers capital K last observations of the low frequency variable. In particular, the values for the Midas component are obtained through a weighting function P, that is the beta one, that depends on two parameters, omega-1 and omega-2. In particular, these parameters allow to differently weight more recent observations by imputing a smaller weight to older observations of the low frequency variable. And this is done by setting omega-1 to 1 and by optimizing omega-2. So what I did to develop my model was to exploit this framework. In particular, I denote with a capital T, the original training set used to train the quantile regression forest that is made by daily observation of the dependent variable and daily observations of a set of covariates. And what I did was to use to compute a Midas component for each low frequency variable that I want to consider in my model and use them as additional covariates in the training set. The aim of my model is obviously to deliver the optimal value at risk forecast, but also to find the optimal vector of parameters omega-2 for each Midas component. And in particular, the optimal values are set to minimize the quantile loss by Gonzalez-Vera, which is a derivable version of the original quantile loss function. In particular, the optimal vector of omega-2 are found via grid search. Regarding the empirical example, which has been like a small application for this model, considers the computation of 300 predictions of value at risk for the Standard & Poor's 500 index by considering as daily covariates the lag of the returns, as well as the lag of the VIX index, which measures the volatility of the Standard & Poor's index. And then I've considered two low frequency covariates, which are the monthly industrial production and the monthly consumer price index of the United States. In particular, I've evaluated the performance of my model in terms of value at risk, like I already did with the other model, by by running backtesting procedures and computing the quantile loss. In particular, differently from the other model, I've decided to consider a small set of covariates because I've decided to compare my model with traditional statistical models that usually do not allow to consider a large amount of covariates. So obviously, if I would have considered a model with a high number of covariates, it would have been natural that my model would have performed better than the other ones. So I've used the same set of covariates for both my model and these competing models, which in particular are divided into classes. The first one are the classes of models that do not allow to consider low frequency variables, which are the standard quantile regression forest, the quantile regression, and two specifications of the Garch model. And the other class instead considers 4 different specifications of 2 models that allow to consider low frequency variables, which are the Garch-Midas and the double asymmetric Garch-Midas, each of them considering one low frequency variable. So here you can see the results. So in terms of a percentage of the ratio of losses, my model delivers the smallest quantile loss. As you can see, this percentage is below the threshold of 100. And also in terms of quantile of backtesting procedures, my model delivers statistically adequate VAR forecasts. So in conclusion, what I did in this month is to develop 2 models, one based on computing dynamic quantiles and the other one based on combining the mixed data sampling approach with the quantile regression forest one. And in terms of empirical application, both of these models outperform existing models. What I'd like to work on in the next months, in particular, is the development of a dynamic Midas quantile regression forest, which would allow to consider both mixed frequency data and model dynamic quantiles, as well as treating mixed frequency data not by using the Midas sampling approach, but with neural networks through under a missing data imputation approach. So these are the main references, and thank you for your attention. And if you have questions, please feel free to ask them.
Thank you, Mila. Any comments or questions? One comment that I have, so clearly point of attention, it's a very robust, of course, project. One point of attention is somehow not to stay too much confined. I like the last line you had in the conclusion, no? To your preferred kind of models and comparison between likewise models, because in a sense, the thing the one would like to avoid is to be producing hammer in search for a nail. No, it's a new, let's say, variation of known models that don't really find a extremely strong motivation in real examples. I see you have this kind of sensibility. I would encourage you to somehow to look for what is really needed and why your proposals are let's say, solving some important challenges, and also comparing with different like-minded approaches, like you mentioned, of course, neural network, deep learning, whatever. I mean, let's try to somehow focus on the diversity of approaches that we might come up with, so to make approaches that are more robust and general, in a sense, generally applicable. Do we have any other questions or suggestions?
Only a quick curiosity, Dino.
Yes.
So what are the tools you're using for this evaluation? So you're using, how are you carrying out these evaluations you showed, these results? I mean, in terms of software or frameworks, I don't know, mathematical frameworks.
So you're asking about how I evaluated the results in terms of statistical adequacy?
Yes, so you implement that in some language or, yeah.
Okay, no. So I've used R, the R programming language, because it allows, I mean, it's more suitable for statistical applications, especially not for my application, but for the application of the other models. So it has been easier for me to run the classical statistical models instead of export everything in Python. But yeah, obviously.
Yeah, sure. No, it's very, very commonly used.
Yeah, no, especially for the statistical tests.
You don't run into any. I mean, you don't have to analyze massive amounts of data when analyzing these models or comparing them. Just was curious how long it takes to make these evaluations.
Okay, so generally the generalized random forest, regarding the first model, the generalized random forest application takes more or less 5 minutes. It's super fast, especially because I use an reiterative approach, recursive approach. So instead, for the quantile regression forest, it takes longer. It takes the 38% of time more. But the main difference I found, and which actually was something that I was a little bit scared of, it's that even if we are talking about a machine learning model that should take a greater amount of time to be trained, actually my model, it's definitely faster than the recursive computational bilat-twist with the caviar model. So also this represents something that I wanted to focus on, because I mean, you can compute a super cool forecast, but if it takes you 100 years and a lot of computational effort, it's, I mean, under an application point of view, it's useless, more or less, if we want to say this.
Yeah, thank you. Very clear. Thanks, Mila.
Thank you for the question.
Okay, thank you, Mila, very much for the presentation. Thank you all. We have essentially eaten up most of our break time. So I would say it's 12:04. We really need to begin back at 12:10 because we have the fantastic final four students, Mirko, Jack, Laura, and Valentina. And if we want to end up by 1:30, we need to really stick to the timing. So let's just have a stretch for 5 minutes or so, and we convene back at 12:10, okay, to finish the meeting on time. Thanks, everybody. Very interesting presentations. let's go for the final session of the PhD day. We have 4 more discussions presentation to discuss. The first one is Mirko Nardi, then we have Jack Tacchi, then Laura State, and then Valentina Pansanella. Okay, so we start with Mirko, who's going to talk about, yes, he's going to tell you about. Please, Mirko, the floor is yours.
Hi, do you hear me?
Yes, we do.
Okay, I'm going to share my screen. Okay. Hi, everyone. I'm Mirko Nardi, and the title of my project is Decentralized and Resource-Efficient Machine Learning Methods at the Edge of the Internet. And I'm going to start from my proposal, and then I'm going to show you my progress so far with the help of my supervisor, Andrea Passarella, and Lorenzo Valerio from the IT department of the CNR. Okay. Okay. Okay, starting from my proposal, the objective of my work is building the distributed, decentralized machine learning solution with particular emphasis on Industry 4.0 application. And the motivation behind this objective is that today machine learning solutions are mainly centralized, so they require huge amounts of computational resource, the collection of a huge amount of data, and of course privacy issues. And so the idea is to keep the data on the devices and training an algorithm across multiple decentralized devices. And in particular, this is our starting point, which is federated learning, that is essentially composed by 3 main steps. We have a local training, a synchronization step, and an aggregation. Here the parameter, we have only exchange of parameters, which are the weights of deep neural network. And after the exchange of the parameter, usually there is some kind of aggregation, like an averaging and something like this. And then a global model is shared among all the devices. Of course, federated learning involves many challenges. For example, the fact that the devices at the edge are resource constrained, the topology of the network that can change dynamically, and we cannot assume that the data are identically distributed. In addition to the challenges, there are many open problems as well, and we found them in the annual report of the federated learning. In particular, we found that there is almost any solution regarding federated learning applied to semi-supervised and unsupervised scenario. So we started from this problem, and here a bit of background about semi-supervised and unsupervised task. There is no universal definition in general, but the aim is usually the identification of rare events or observation, which significantly differ from the majority of the data. And we can distinguish between novelty detection task, in which we train only on positive sample, and the test is on new unseen samples. Here the emphasis is to find a model for normality. And on the other side, we have the outlier detection task, which is completely unsupervised, but usually we can do some assumption about, for example, the percentage of the outliers. The emphasis here is dealing with contamination during the construction of the model. It is important to note that techniques often can work on both the task, but with proper tuning or configuration. And so here we have the state of the art of the novelty and outlier detection techniques. This is important because here we can understand the level of complexity of centralized solution. So we have classical algorithm like one class support vector machine, local outlier factor, and so on. There is a recent shift to neural network using, for example, autoencoders, generative adversarial networks, and usually here we exploit two things to set an anomaly score. For instance, the low dimensional representation and the reconstruction error. There are also many recent extensions of these solutions, which are essentially ensembles. For example, here we have essentially a combination of many basic solutions. For example, here we have the freezing of an autoencoder. So here we exploit the low dimensional representation. Here we exploit the reconstruction error instead. And the same can be said for the outlier detection techniques. There are also here many ensemble methods. For example, here we can see that the reconstruction error from an autoencoder is given to a clustering algorithm, or the other one in which the ensemble happens on randomly connected autoencoders. And so after considering the state of the art, we detected some open problems for distributed machine learning in semi-supervised or in supervised scenario, which are, of course, the same. We have the same problem of the federated learning scenario, but this time we have no labels. And federated learning works are mostly supervised. Then there is the multi-class novelty detection. This is because the centralized works focus mainly on training on a single normal class. But in reality, most dataset intrinsically contains multiple categories. But when a centralized solution is considered, the training set is seen as one single class, ignoring the multi-class structure. Then there is the data distribution shift, which means that if we train some normal tests on a particular domain, if we switch domain on the test set, then the model is unable to recognize the samples. So this is our focus so far. So for now, we ignore the data distribution shift problem. And here an example of our work. So here, for example, we take the dataset MNIST with 10 classes, and here we simulate a novelty detection scenario. We select 5 normal classes, and the outlier classes are the remaining classes. And the training set is composed of all the samples of normal classes. In the distributed setting, we have a one-to-one correspondence between normal classes and nodes, and we set a different level of imbalance. For instance, we have two extreme, the ideal imbalance in which every node has samples of one normal class, a uniform in which each node has all samples from all normal class. And in the middle, we set some zip distribution in which a node receives mostly samples from one normal class. And as regards the training in the distributed scenario, we set a small model on each devices, and each model is trained locally. And then as regards the prediction, then we share the trained models, and as regards the prediction, considering a sample test X, The score is considered like the minimum of the reconstruction error among the nodes. We don't have a formal proof of this, more an intuition, but we are working on this part. And on the other side, we have the single class centralized novelty detection, in which we imagine that all the samples are collected in a centralized node. And here everything is trained as one single class, but the model can be arbitrarily large or complex. So this is our main comparison. And we have some preliminary results on 2 datasets, MNIST and Fashion MNIST, and on 5 classes, 5 normal classes, randomly selected. And on the right side, you can see the decentralized model we use. We use 1 class upper vector machine, local outlier factor, and some fully connected autoencoders with a different number of layers. While in the distributed part, we have we set a relatively small fully connected autoencoder on each node. And again, we set 2 extreme case, an ideal case and a uniform case. And in the middle ground, there is the ZIF distribution, the one in the figure here. So for example, considering the normal class 0, 1, 2, 3, 4, and a distributed setting like this, this is the AUX score of this scenario. So here we can see that, for example, for a MNIST, the winner is local outlier factor, but the distributed scenarios works pretty well. The isolated distributed is the second best. While if you increase the complexity of the dataset, for example, using a Fashion MNIST, the distributing settings wins almost always, and this is a very good result for us. So to conclude, yeah, we have very good results, and they are excellent when a class emerges. So when we are on the left side of the table, and the training time is very fast, since we on the distributed nodes we run small models and they can run in parallel. And of course, there is no data exchange, but only the models are exchanged. On the other side, we have made some assumption. For example, we excluded the data distribution shift. So the data among the device has to be consistent. We have a one-to-one correspondence between normal class and nodes, and we have n inference, where n is the number of normal classes. So this is something that this is a constraint we probably try to weaken in the future. And yeah, we want to try more complex centralized model and more realistic use cases. And here there is another missing part, is the federated learning mechanism. Since here we have just one training shot, it's more like federated ensembling so far. So we want to extend this to a federated learning round. And okay, that's it.
Thank you, Mirko. Questions, comments?
Yeah, I have some. Can you hear me?
Yes.
Go ahead, Tommaso. Yes, please.
Yes. So, yeah, Mirko, very interesting presentation. Let me thank you. My question is simply about the performance that you are experiencing. So I understand fundamentally you have 2 major reasons for investigating this kind of decentralized distributed algorithm. So on one hand, you may want to not exchange the individual data samples for various reasons. On the other hand, there is fundamentally a performance opportunity to distribute the computations as opposed to keeping it centralized in in a cloud data center or something. So in the case in which you are saying, okay, distribution works really fast, did you, or are you planning, or at least I would recommend?
It's a little bit low. Can you?
Yeah, I would consider at least trying to consider different settings in terms of the computational capability of your edge devices. Because if you, I don't know if now it's louder, so if your edge devices are really resource constrained, I mean, if you are talking about a sensor, for example, a temperature sensor that is supposed to do some local computations before sending out before exchanging models with the rest of the network, or if you are talking about a smart camera that, you know, besides acquiring each frame in a computer vision, is supposed to do some local federated machine learning computations, etc., is one thing. If instead you have a relatively powerful computational node with memory, with a lot of memory, then it's a completely different story. You know, in some cases, you know, people in the world of cloud, edge cloud, or cloud computing, they often mention cloud acceleration, in the sense that normally you make things faster by sending them to a powerful cloud server and getting back the results, you know, which can be computed much faster. So just, you know, what are your considerations or any plan in this regard?
Sorry, I'm a little bit lost about the question. Could you repeat it, because I missed some parts, I think.
Yeah, so it's basically about the computational power of your edge devices has to be carefully considered, because your edge device can be really it can have really poor computational capabilities. It can be mobile. It can have, you know, power constraints, fan constraints. Very often you have devices which have to be fanless. So they cannot generate heat, so they cannot have much computational power. And in this regard, it's not clear, you know, what are the optimum trade-offs of how you can actually split at best computations between, you know, a decentralized and decentralized algorithm.
Okay, this is a good question, because in fact here there are some missing results, and that we roughly already calculated something, but we have also some results about we have some statistics about, for example, the number of layers, the number of connection, and the amount of data exchanged. So once we combine this statistic better, then we can do some consideration of which is the switching point from a distributed to a centralized. So in short, we don't have an answer to this. It's something that we need to investigate more, and for now we try just to run some very light model on the we assume that they are pretty weak devices, and we cannot send to, we assume that we cannot send them for various reasons to a centralized cloud server. And so it's something that we still need to understand how to.
Yeah, also remember that a centralized cloud server can actually distribute computations across multiple machines. So if you look at the problem from a purely performance perspective, you should consider that, you know, a cloud provider may be really powerful in certain things. So just consider also this aspect if you look at performance. Then of course, if you consider the data sensitivity, or you cannot transmit data for whatever reasons, then of course it's completely different. Yeah.
Essentially, we are hiding behind the privacy issue for now, but yeah, it's something that we have to deal with for sure.
Well, one aspect that we really need to proceed with Jack But one comment I wanted to stress, you had in your final slide, relaxed the constraint that, let's say, there is no data shift, different distributions across different devices. And I believe that this is really something in perspective to be relaxed, in the sense that what is particularly interesting in many real world application is that a distributed user may have different perspective on a phenomenon. No, it actually sample from different distributions or from different situations, and this is something, let's say, challenging and important. And I see this as an interesting aspect of your research.
This is something that we probably will touch in the future, and yeah, there are many aspects of the. In general, this is I think a subset of the non-AD data distribution. So there are many aspects about this.
It is actually one of the issues that makes the distributed setting, the centralized distributed, fundamentally different from the centralized one, in a sense. So it's, I think it links to the comments by Tommaso Cucinotta, actually. Okay, thank you very much. Yet another interesting presentation, and we now proceed with Jack Tacchi. Jack, the floor is yours. Jack will talk about sentiment of social ties.
That's correct. Can everyone see my slides?
Yes.
Yes, good. Yeah, so as Dino said, I'm looking at the sentiment of social ties, and sort of specifically how natural language processing, specifically sentiment, can be used in online social network contexts. So yeah, my supervisors are Andrea Passarella, Chiara Boldrini, and Marco Conti. This is all sort of based off this social brain hypothesis that was coined by Dunbar in the 90s. And what this basically says is that our ability to process information is determined by the size of a part of our brain called the neocortex. And what the ability to process information really affects a really wide range of abilities and tasks and so on. Most pertinently here is the group sizes and the complexity of the social groups that we can maintain. So what this is saying is basically we have this innate hardwired limit that is based on the size of our neocortex, hardwired, after which we are unable to maintain groups, social groups as humans. And they will sort of begin to fragment and become unstable if these groups become too large, because we just don't have the cognitive capacities to maintain them. Of course, from an evolutionary point of view, there's a huge advantage in being able to maintain larger groups. For example, if you have just one caveman going around hunting, having to defend himself and find food, he's not going to be able to achieve anywhere near the same number of resources as, say, a group of 15 or so people doing the same thing, but working together and pooling their resources are able to do. And this effect between the neocortex size and specifically the ratio between the size of the neocortex and the rest of the brain has been found not only in humans, but also in other primates and different species of mammals and also birds. So we see this quite distinct line connect the relationship between the neocortex ratio and the mean group size. And if we extrapolate this out based on the findings from all these other animals, we find that humans should have roughly a 150 group limit. And this has found to be the case for many traditional types of groups, so like hunter-gatherer tribes and small-scale horticultural societies, where these are sort of societies based off things where everyone knows everyone else and they're able to maintain the connection. Not like modern societies where we're able to live in a city without knowing the vast majority of people we're actually living with. Now, in online contexts, of course, there's been a lot of modern technology around that allows us to communicate a lot more easily, from phones to Facebook to Twitter and so on. Now, you might think that this makes it easier for us to maintain social groups and that therefore we can maintain larger groups. However, this has been found not to be the case. And despite all of these modern technologies, we're actually still limited by these innate cognitive limits. So for example, here we have a chimpanzee. If he managed to go on and start using Twitter, he wouldn't be able to maintain as many active friends as a human would. Again, humans would be around 150 at the max. This chimpanzee maybe 75 or 80. But what this does mean from the research point of view is that as these online and offline social networks are very similar, they also have similar properties, we're able to study them in multiple contexts. And what this means is quite a nice symbiotic relationship between traditional cognitive scientists and the more modern online social network research, where we have these established theories and models that we can take from cognitive science and apply to the research into social networks. And equally, there's these immense amounts of data and new possibilities that wouldn't otherwise be feasible because of these modern technologies. So for example, if we wanted to collect a data set from say 20 people, traditionally we would have to go and interview them, conduct surveys, and spend weeks and weeks and weeks collecting all this data. Whereas nowadays we can just go online and download, say, the last 3,000 interactions they've had over the last, say, 6 months or so. So clearly it's a lot cheaper, and so we can explore new avenues that otherwise weren't possible due to time and financial constraints. Now, one way of looking at these social networks is by taking an individual and putting them at the center. This individual can be called the ego, and all the people surrounding them, we can then organize into these hierarchical circles, where at the center we have people they contact, a few people who they contact very frequently. And as this gets, the circles go out and further out, they will have less and less contact with them. And this has been found in both offline and online contexts to be a very common structure to be found. For instance, say if we have this one for a human, in the middle we have this support clique with roughly 5 people. These will be people, say your close family or your colleagues who you are seeing every day, you probably get on well with and just spending a lot of time with. And then to say sympathy group, the next one out. These will be people you see maybe once or twice a week who you sort of know, you will have a chat with if you bump into them in the street. But you don't see them as often as, say, as a partner or a colleague. And as we get out and out, we come to the largest one, which is the active network. The largest one in this model is the active network. And these are people you sort of know, but perhaps you maybe see them once a month, or you don't spend huge amounts of time maintaining the relationship with them. And as you can see, usually what we find is that each of these circles is a sort of larger by a factor of roughly 3 each time. Now, the way we organize people into these groups is based on their relationship or their tie strength to the ego. And traditionally, this has been measured using only the frequency of interaction between these 2 individuals. And although this has been shown to be a good approach, there was a seminal paper by Granovetta called the Strength of Weak Ties, in which he defined the tie strength as the equal combination of 4 key things, which are the time spent maintaining the relationship, the emotional intensity of the relationship, its intimacy, and the reciprocal services between the 2 people. Now, so the frequency of interactions clearly is being measured by, is measuring the time spent on the relationship. However, although there have been studies showing that all 4 aspects are correlated, the other 3 are not being directly measured. And that's why I would like to introduce natural language processing, which has been previously established in a wide range of areas, also including social media, and specifically within the areas of sentiment analysis and measuring the emotional intensity of tweets. So this introduces a new way to actually not just indirectly, but directly measure another 2 aspects of Granovetta's definition, which were hypothesized to all be contain the same amount of information or to be equally weighted. So there's potential for a lot more information to be introduced into this ego network model. On top of this, the introduction of NLP will allow for the introduction of negative connections as well. As before, only using the frequency of interactions, it's not possible to have a negative frequency. So if we have negative sentiment, we can therefore have negative connections. Negative links have been shown to have a significantly large amount of information, which is often information that's different than we would have access to with any positive links. If we take the example here, we have 2 graphs, one on the left, one on the right. And if we were trying to detect the communities within this graph, perhaps the left, it might be a little bit difficult, but we can see between the different communities, there are sort of fewer connections, and within the communities, there's lots of connections, there's sort of tightly knitted things with few strands between them. However, on the right, it's a little bit more complicated. They're more interwoven. However, if we had negative links, we would expect the majority of negative links to be between communities, which means it'd be a lot easier to separate these three communities out, even though there's a sort of a bit of a mess here. So there's quite a bit of a potential for this sort of introduction of negative links. And of course, as humans, we don't get along with everyone. Sometimes there are people we don't like. We have negative relationships with them. And this has been found to be the case on social media sites as well, despite the fact that you cannot usually mark someone as, say, I guess the equivalent of Facebook would be as marking someone as an enemy rather than a friend. Of course, there's all sort of marketing and ethical reasons why this would be the case. However, it's kind of annoying as a researcher because we cannot directly go and grab these sign networks, which provides some extra information. We have to make them ourselves, which is what this proposal is aiming to do. So again, the proposal in a nutshell is, can natural language processing be used to extend our understanding of the ego network model? So the introduction of these two extra elements from Granovetter's definition, what sort of extra information does this provide? And then specifically going on to the introduction of signed connections, how does this change the ego network, its structure? Do we see that there are extra circles that only contain negative links? Is there like a regular, again, this sort of increasing by threes distribution of negative links throughout each group? Or are there only certain groups that have negative distributions? And if these are the cases that they are different with the introduction of the natural language processing, what sort of benefit can it provide to tasks such as information diffusion and community detection that are both common tasks within network sciences? So far, my work has mainly been on data procurement and pre-processing, and I've been mainly using Twitter and the Twitter API. The reason for this is that it contains 192 million daily users that are contributing to 500 million tweets per day, and around 20% of this is communication data, meaning there's someone mentioning someone else or replying to someone else. So these are clearly relationships that are online and that are fairly easy to access. One downside of Twitter is that it's not just humans that use it. There are lots of groups of people, say like businesses or companies, and also a lot of robots and spam bots and all these sorts of things. So I've also been using this Botometer application, which is around 99% accuracy, to remove a lot of these spammers. The reason there's such a high accuracy is because it cross-references not only the information from the individual accounts, but also external lists of self-declared bots and reports of accounts being bots. This doesn't, unfortunately, remove all the irrelevant accounts. We're still left with these businesses. And as you might expect, an account being run by a group of people or a marketing team, say, does not have the same cognitive limits as an individual. So it's sort of irrelevant to this, this research. So I put a non-human classifier, what I call a non-human classifier, which will separate out individuals from others. And this was based on previous work. It was a random forest that sort of managed to gain 85% precision and 84% recall, which is slightly up from the previous research, which was around 81, 82. And I think this slight increase is just due to the fact that I cut out a lot of the perhaps more difficult tests from using Botometer, which was not done in the previous work. Next, I've been working on a data set containing 1,000 interactions between people on Twitter. All these interactions are between two individuals, so there's 2,000 individuals in total. And this is currently being annotated by some English native speakers that I've recruited from the University of Kiel. And this annotation methodology is based on previously established research. So they are going to be saying if each conversation is positive or negative or neutral. And then hopefully I'll be able to use this data to train a classifier that can then predict the sentiment of these ties and therefore the signs of the ego networks coming from these people. And of course, in order to create the ego networks, we need to collect some data on the Twitter timelines. The timeline is just the collection of the last, well, of all the tweets from an individual. So I can see all the interactions they've had with anyone else. And I've sort of been collecting all this data, filtering some of it out. For instance, say if an account hasn't had time to fully develop its social network online, maybe it's just started a few weeks ago, or it's only, for example, if we say my account, I do have a Twitter account, but I use it, maybe once a week, maybe once every 2 weeks, and I usually just read other tweets. I rarely post anything myself, so my account will be useless for this, as I haven't built my own social network online. So once all this filtration is finalized, I plan to carry on doing more of this ego network analysis, but already we can see that there are some similar results coming out. Whereas on the left, we have some previous results from previous research. You can see that usually the number of circles we find is 3, maybe usually 4, sometimes 3. And I'm sort of getting similar results. I'm expecting this will conform more once the filtration process is complete, as I still have a few steps to implement. Yeah, so again, just to summarize, that's my current progress so far. I've been mainly on data collection and pre-processing, and also building this non-human classifier to separate out the companies and so on from the regular people. And the steps I need to still carry out to continue this analysis of the unsigned ego networks. Then once the annotations have been completed by those students from Kiel, to create a sentiment predictor, then to use that to convert the unsigned ego networks to ego networks, and sort of analyze and compare those to see what differences they have, and see if there's any extra things coming out, again, say, due to the negative links. And then I want to try and test the unsigned, or compare the unsigned and signed ego networks to see how they perform with various tasks, such as information diffusion and community detection. So yeah, I did have 2 brief slides on my study plan and my supervisory panel so far, but I think in the interest of time, I will just skip over these, just to make sure we're not any far behind. And these are, again, my references. So thank you very much. Please let me know if there are any questions.
Thank you, Jack. Very interesting project. I wonder if anybody wants to ask questions or give comments on this. Let's say, it's very ambitious, and I like the let's say the design of your research. I wonder whether you have other ideas for potential other data sets which might be even more adequate than Twitter in the sense that, of course, Twitter is a good tool because it's has the possibility of having also, let's say, open data compared to other social networks, but at the same time is not the typical social network that people use for personal communication, right? It's more rather, let's say, how do you want to cope with that kind of difficulties?
Yeah, that's true. So I did look at a few different data sets when I started this, and the main reason for choosing Twitter was just because of how much easier it was to access the data compared to other places like Facebook, which has of course come under fire recently due to some sort of privacy issues, and so they've been a bit less eager to share their data with just anyone. And yeah, it doesn't maybe represent a social network quite as well as Facebook does, but it has sort of been established in research previously to sort of be acceptable with this kind of research.
It will be probably interesting to see whether, given the interest in the research, you may also find some kind of agreement with other, with more social network platforms.
Yeah, absolutely.
That would be cool. But thank you very much. If there are not other comments on Jack's presentation, we thank him and go forward with Laura. Laura State. Thank you, Jack. Laura State is the second PhD student of our PhD that is also part of the No Bias ITN Marie Curie framework. And Laura, it's actually up to you. The floor is yours.
Thank you very much. Can you see my screen in full mode?
Yes, we do.
Okay, perfect. Thank you very much for the nice introduction. So I'm going to talk about my PhD thesis, or what I hope I can do in the next 2.5 years, under the title Logic-Based Approaches to Construct Meaningful Explanations for Machine Learning Systems. I'm Laura Starter. I'm a PhD student here in data science. I'm also an ESR in the No Bias project, and I'm in the KDD lab at the university. So why is it necessary to compute explanations in the first place? Well, as much as we know that machine learning has a huge positive impact on our lives, we also see that it can have a negative impact, especially for people who are already in marginalized groups in the society. So for example, there's a commercial face recognition, which showed a gender and a racial bias. And similarly, we know for crime recidivism prediction that there's some racial bias. Also, I want to bring to you the example of the Uber self-driving car, which killed a pedestrian. So in all these cases, it's quite important to think about the moral values which we can give to machine, or to what extent this is possible, but also to think about accountability and responsibility. So who is held to be responsible after something negatively happens? And it's quite hard to think about these questions because most of the systems behind these automated systems are machine learning systems, which were quite accurate, but are usually quite opaque, so we cannot understand them. So in the last years, we saw quite a surge, quite a rise of the field explainable artificial intelligence, or alternatively interpretable machine learning. And I want to give you a very quick overview on the field. So usually we have two different types of approaches. On one side, some researchers focus on transparent box design, or alternatively, it's called white box model design. So they try to construct interpretable approaches from the beginning. On the other side, researchers focus on black box explanation, which is also important if we consider an industrial scenario. So even if an corporation might use a transparent box to predict something, and they might not give out all the data about this system because of some intellectual property right, and then even these black box explanation can be utilized. So there are also a multitude of different approaches in the field, and I brought you two just exemplarily. So the first one I want to present is LIME. So LIME explains prediction locally, meaning for one single data instance, which is usually one single person. So what is LIME doing? I'm having here a picture on the lower left corner. So LIME is locally approximating the decision boundary, which can be, in theory, arbitrarily complex by linear regression. And then using the weights from the linear regression, it is creating an explanation for this specific local data instance. Another example I brought to you is from the image domain. So this, you can see this example with the giraffe and the trees behind. What the DNN is doing in this case is generating some caption. So the caption for this picture is a giraffe standing in the forest with trees in the background. And the explanation which is given here is an attention map. So you see in the second picture, the right-hand picture, that the background of the giraffe is whitish. And this is the area where the network is focusing upon. And this is delivered here as an explanation. After reading a lot about this field and surveying the field, I put together some of the challenges I see in the field of explainable artificial intelligence. So the first challenge I formulated is that up to now, there's no canonical definition of what a good explanation is, and also what its desiderata, also in terms of legally, desiderata are. A second challenge or second questions I formulated is what are the implications for non-stationary machine learning models, and how can we encode this time dimension into the explanation framework? I think this is particularly interesting because in the real world, models don't stay the same. So you have, for example, new data coming into your model, and then the model has to be retrained, and then you have a change of the model. Thus, also the explanations will change. So to some extent, you would need to incorporate this time dimension into your framework. Then I formulated two more questions. One is about the use of existing background knowledge to enrich explanations. And the last one is about the evaluation of explanations. In my PhD, I hope that I can answer or try to answer some of them. And I want to do this with logic. So in that sense, logic could serve as a tool to answer some of them. And before I go a bit more into possible pathways for my PhD, I want to give you an introduction to logic very quickly and very briefly, just for you to have a better idea. So I brought you this example of inductive logic programming, which is basically the backbone to logic-based learning. And I have here a small data table, so you can see some data subjects, and these data subjects have each 2 features and then 1 label, which is whether these people are happy or not. You could imagine now a typical machine learning scenario where you would build a predictor about these people and whether they are happy or not. However, what we want to do is we want to learn this by utilizing logic. So in the first step, we need to formulate our knowledge. So we need to formulate it in 2 ways. On one side, we need to construct some background knowledge. So you see this in the left-hand side. So this background knowledge contains information about these different subjects. So for example, that Alice is a Lego builder. Also, we would need some examples. So we need a set of positive and a set of negative examples. In this case, we have 1 positive example, which is Alice, and she's happy. And then we have 3 negative examples. And then the role of inductive logic programming or logic-based learning would be to learn a hypothesis. In this case, this would happening by searching over the possible hypothesis space. And then the hypothesis is formulated such that if you take the hypothesis together with the background knowledge, only the positive examples logically follow. So in this case, we have the hypothesis of all elements which are Lego builders and which enjoy Lego, they are happy. In this example, you can already see some advantages of logic in general and also logic-based learning. So specifically for logic-based learning, it works on very little examples. So here we only have 4 examples and we already get a correct hypothesis. And we also have some correctness guarantees in terms of logic-based learning. And then another advantage I want to show, I want to mention is that logic-based learning on general logic is quite interpretable. Even maybe in the beginning, it's not super easy to read these logic statements, but in general, we always know what's happening in logic-based systems. So on the next slide, I give you an overview over possible approaches to interpretability, which already utilize logic. So I see them again as a toolbox from which I can draw tools to then build my explanations. So I already talked about logic-based learning, which is rather slow or reasoning-based. And in case you know this book by Kahneman, this would be system 2. Opposed to this is machine learning, which is rather fast and perception-based. So these two fields kind of builds the backbone of what we call artificial intelligence. There are also some approaches which lie in the middle, so-called neurosymbolic approaches or statistical relational learning. And then we can also look a bit more into the field of machine learning, and we would also already find some approaches that utilize some ideas from logic. So there is some interpretable models such as decision trees or rule lists or rule sets. And there are also some explainers which already work in the logic domain. So there's LoRa or G local X. And then we also have case-based reasoning in terms of counterfactuals, which is quite similar to utilizes some ideas from logic. And then I also want to mention 2 more tools from logic, which can be helpful for my research, which is first constraint logic programming and second argumentation. Okay, now I gave you this background. I want to show you possible pathways for my PhD. So I put them into 4 main columns. The first one should be a verification of explanations, specifically counterfactual explanations. And I want to give you some details on this on the next slide. A second point should be the comparison of explanations over individuals, which could answer questions about individual fairness. So the idea that if you have similar data subjects, they should receive first a similar decision and then also a similar explanation. And then another core part of my PhD should be comparing explanations over time. So this relates also to what I said before about non-stationarity of models and adding this time dimension to the explanations. And then the first part should be explanation, presentation, evaluation. So I think with respect to logic, what we can utilize here is if we have an already formulated explanation theory in logic terms, we can relatively easily specify these explanations for the respective target user group. And then, of course, we need a solid evaluation of the developed approaches. Okay. As promised, I wanted to talk a bit more about verification of explanation. specifically about counterfactuals. So what is a counterfactual explanation? Counterfactuals are answering what-if questions. So I'm applying for a loan, I'm getting rejected. I'm asking, what if I change my monthly income by adding 500 per month? Will I then get the loan? So this is asking these questions. They can be computed without looking into the model, which makes them quite popular. Also, there's some support by research in the social sciences that people receive these explanations very well. So it's also quite very likely that people will like these kind of explanations from the XAI side. And there's a close relationship to algorithmic recourse. So algorithmic recourse, rather than trying to understand algorithmic systems, focuses on giving agency to people. So giving people advice, actionable advice to change, to alter their future decision. Okay, I also brought to you a specific example. So this is from a loan application scenario about a data subject. So he's 22 years, he's male, and he has an income of 800 and no car. Now we can use LoRa to extract a rule why this person was rejected in a loan application. And Doris says because the age is smaller or equal to 25, because he's male, and because his income was smaller or equal to 900. Now we could also ask the same system for counterfactual, and it would give back two counterfactuals. The first one would be to increase the income over 900, and the second one would be to change the gender. In case of the second one, this is of course not possible, and this points into two directions. So the first one would be because this also specifically focus on a protected attribute, which is gender in this case, this would point towards a possible bias. So one could think about further evaluations here, and it also undermines this function of explanations to detect bias in the decision pipeline. On the other hand, this is the specific point where I would like to start my project. So I would like in the counterfactual generation process to add some constraint, which specifically would not allow for these changes. So I would like to add some constraints which follow either causal connections or just a simple fact that you cannot change your gender, you cannot change your age to a lower age, and so on and so forth. And I would like to do this by utilizing constraint logic programming. So you already know this picture. I already spoke about the 4 first boxes and a bit more about counterfactual explanations. I added 2 more boxes here in red because I think there are 2 more aspects which are important. The first one would be legal aspects of explanations. So you probably know there's a GDPR stating this right for an explanation. However, I think it's important to look a bit more into detail onto this. So one aspect I would like to focus upon is what are the exact legal desiderata for an explanation to be also valid in a legal setting. And because I want to build an explanation which later can be potentially utilized in court. And I also would like to do this, or parts of this should be done during my internship next year at the law department at University of Southampton. And then there's another red box, which should be about real-world use cases. So of course, I would also like to evaluate my framework. And I can possibly do this in the insurance sector during my last internship at Generali in 2 years. Okay, thank you very much for your attention. And now I'm happy to answer all your questions.
Thank you, Laura. Very nice and clear presentation. Any comments or questions for Laura? You know, one comment that question that I have is that I really like the fact that we should investigate logic more extensively, because it's certainly a very meaningful language in many fields. No, especially when we reason about decision. Are you considering, let's say, only working on, let's say, the explanation that are traced back to the original variables that are available on the data, or are you also considering somehow possible other sources of information like latent spaces or let's say, concept spaces that could be superimposed to the observable ones?
So for now, I would focus on only on these features we have defined. So maybe I show the slides, but yeah, you're 100% correct. So there are other approaches, and potentially they can be also utilized. So yeah. So especially, for example, if you look into neurosymbolic approaches, I think there's quite a nice world outside.
Okay, but yeah, it's a fascinating project. So I'm very happy that somebody is working on rules and logic-based approaches. Very nice. By the way, one little piece of advertising. Today in the afternoon at 3 p.m. There's a very nice seminar at Scuola Sant'Anna within the let's say the data science part of Scuola, where Professor Francesca Toni from Imperial College will be lecturing on argumentation and explanation. So it's something that is closely connected, right? You mentioned argumentation.
Yeah, I will be there as well.
So it's a good, let's say, appointment to deepen on these topics, and everyone is actually invited to join. Francesca Chiaromonte sent the possibility. You can both attend physically if you're in Pisa, or you can attend online if there are instructions in the mail sent out by Francesca Chiaromonte. Thank you very much, Laura. Very nice project. So let's move on to the last but not least of our presenters today, Valentina Pansanella, working on network dynamics of opinion formation, opinion diffusion. And
hi, everyone. I don't know if you can hear me.
Yes, we do.
Okay. I'm sharing my screen. Okay, can you see the presentation?
Yeah.
Okay.
Yes.
So good morning, or it's actually afternoon, everyone. I'm gonna present my PhD project proposal, which temporary title is High-Order Effects on Opinion Formation, Networks, Dynamic, and Biased Agents. I'm gonna start with a brief overview of the problem, sum up of the state of the art, my project proposal, and some limitations. So in the wide context of studying how opinion form and evolve in society, which is a complex and crucial task, of course, I would like to understand to what extent online social networks and media have changed the way people exchange their opinions and how they diffuse over these new contexts, contributing to nowadays opinion polarization. Why is it important, the task of understanding how opinion form and evolve? Because of course, opinions shape our individual behavior that eventually shape the collective behavior of a population, of a society. We recently saw what happened with the COVID vaccine. The shift in opinion eventually affected our healthcare system and eventually will affect also our economy during this pandemic. So it is crucial to understand why maybe this opinion shifts or opinion extremization happen inside a population. So my goal, the broad goal, is to combine theoretical and data-driven studies to gain more insights into the process of opinion formation, focusing on online social networks. The focus on online social network is not only because, as someone said earlier during the presentations, they offer a huge amount of data that wasn't available until recent, specifically on the dynamics of opinion. So texts from which we can retrieve the opinion, social network, etc. But also because these new contexts that are widely used by people to discuss, so to exchange opinion, have changed the way people interact. So here's how I plan to tackle this goal, but before, a brief survey of the state of the art of opinion dynamic modeling. Opinion dynamic modeling is an interdisciplinary field because, of course, opinion formation was studied, first of all, by sociologists, but now it is the main interest of also mathematicians, computer scientists, and physicists, because they create this theoretical model that simulate the opinion exchange over a population of over a network to try to explain the collective behaviors. So mainly they use networks to simulate the interaction of people, and they use rules as in simple equation to simulate sociological theories, like for example, peer pressure, confidence bound, or backfire effect, etc. As I said, there is a very vast literature, especially in the last decade. There were a lot of different opinion dynamic models, each one of them trying to model a particular aspects of the opinion dynamic process. And they are pretty good in explaining real phenomena, as in we can see some patterns in the models that we see also in reality. For example, agreement, going from fragmentation to consensus, etc. But these models are all very simple to understand, meaning that it is clear the causal relationship between the rules established by the computational social scientists with the effect. But sometimes they are too simple. There are a few adaptation of the classical opinion dynamic models to more complex structures that actually simulate reality in a more precise way, such as dynamical networks and higher order systems, because, for example, the dynamics of the underlying structure is very crucial. Interaction networks are not static, are not stable over time. They vary and their dimension shifts over time. And also there is a lack of real data study. There are some comparisons between the results from the model and patterns in real data. For example, maybe we can compare the outcome of a simple voter model where people have to express their vote on something, which can be yes or no, or positive attitude, negative attitude, to, for example, election results to simulate or forecast the results of an election. But there is no quantitative, there are no or very few quantitative analysis on data or data-driven studies in the field of opinion dynamics. And this is one of the greatest issues of this field. There is a great theoretical proliferation of studies, but few data-driven works. So my project proposal, as I said at the beginning, is to combine theoretical and data-driven works. So the workflow of my project would be to still continue to study new models, but also creating a positive feedback loop between the modeling and the validation of the models on real data. So from the models, we can pose ourselves new research questions to gain new ideas to validate on the data. And from the data, we can also gain new insights. Then we can again simulate on the models, maybe to make predictions, or also to simulate the effects of some countermeasures, so that maybe when we see in the population some undesirable behaviors like extreme polarization, for example, we can simulate some countermeasures. So the starting point of this work was a bounded confidence algorithmic bias model. The focus on algorithmic bias inside the focus on online social network is because it is argued that the presence of recommender system and filtering algorithms has increased nowadays opinion polarization on a wide variety of topics, and but it is not yet established if and how these filtering algorithms actually augment opinion polarization. There are, as I said before, only theoretical studies. So my plan is to start by studying theoretically how algorithmic bias affects opinion dynamics on higher order structures and also dynamical networks. So going towards more complex settings than a mean field study. And then I want to also add additional element into this process, which is very important, which is external information. So, for example, the presence of mass media, because in the majority of models, the results of opinion dynamics is the peer-to-peer interaction results. But actually, in real life, opinions are mass media, news, external sources, information has a huge impact on the formation of a personal opinion. In the validating side of the project, we plan to start small, so with the testing of models hypotheses on real data, because some models have very strong assumptions, sometimes too strong, or that comes from sociological theories that haven't been yet validated or on real data. And in the end, the broad goal would be to be able to validate an entire opinion dynamic model on real data. So currently we're working on 3 different projects. One is the algorithmic bias model on complex network. One is the addition of mass media in a mean field study on the algorithmic bias model, and then a confidence-bound temporal evolution studies. As for the algorithmic bias in complex network models, we started from the mean field study, and then we added a more complex underlying topological structures. So we studied random networks, skill-free networks, and also networks with a pre-known community structure to see how these different topologies may influence the evolution. And we actually almost finished writing a paper we will submit to the complex network conference. And in the case of the addition of mass media presence in the algorithmic bias model, we are at the beginning of this new study in the context of the project Human AI, where we added a few amount of mass media modeled as stubborn agent inside the network. And we actually saw some preliminary results that show that, of course, they deeply affect the results we would have without the presence of these stubborn agents, because at some point they start polarizing the population towards the opinion they propose. In the end, we started very recently working on some Reddit data on political discussion on Reddit, which is a famous social network. This study was intended to analyze if there were bounded confidence inside this political discussion and how bounded confidence will be distributed across users and over time. We have some preliminary results which show that bounded confidence, for how we estimated it, is pretty constant over time, but it's actually different for different politically aligned users. So it seems that left-wing users are more open-minded than right-wing users, and that neutral users are the most close-minded ones. So this is what we've been doing up until now. For the future, as I said before, in the modeling side, we want to explore higher order structures and dynamical networks. And also, as I said, as soon as we have some new results, new insights from real data, try to integrate them into a new model. And in the validating side, we want to, first of all, define a suitable methodology to test hypotheses and validate the models on real data. And of course, the goal is also to get access to more data. The ideal, of course, to see if there is and what extent there is the algorithmic bias, for example, would be to have the whole timeline of each users, and also to have, for example, longer time span data, because the opinion evolution process is, of course, very slow, and more fine-grained data in also in a time sense, so have punctual interaction and opinion shifts. Some limitations of this work are, of course, having access to suitable data to validate the models, because we would ideally need a lot of different kind of data. So the social networks, the action the user performs, their timelines, the content they produce, maybe also some personal user features could be useful to understand different kind of dynamics, etc. But also some problems may come from the fact that until now we we transformed the opinion of the users into a numerical value using sentiment analysis and opinion mining. And of course, this process is prone to error. And then also estimating the model parameter is prone to error. So data becomes at some point dirty and there is a lot of noise. And also using this kind of data may arise some privacy and ethical concerns. So some possible solutions are, of course, focusing on the modeling side if data are so difficult to get, and also to find proxies for opinion from different contexts that are different from textual data, so that we don't have to perform sentiment analysis, and maybe in some kind of contexts there are opinion proxies that are less prone to errors. So in the end, I'm focusing on online social networks and with the presence of algorithmic bias. And the workflow basically consists in a positive feedback loop between developing new models and validating them on real data, and to try to explain in a better way reality and opinion polarization. So I think it's everything. Thank you. If you have any question, I will be happy to answer.
Thank you, Valentina. Any questions or comments for Valentina? One thing that I have is that would you think it, of course, also in your case, like in Jack Tacchi's case, there is an issue about having good data for somehow trying to do this very ambitious but very right way of connecting model-driven and data-driven research in a field where I totally agree with you. There is a lot of theoretical work, but very little empirical work. So we don't really know in real social network what kind of polarization trajectories are there, what is the real effect of, let's say, algorithmic bias and the different kind of bias mechanism that can be introduced in platforms. One thing I wanted to ask you, do you think it would be meaningful or possible within the time frame of a PhD thesis also to set up some, let's say, real experiment with volunteers, that somehow try out somehow and share their opinions shifting over a period in different regimes? It's a science fiction, or do you think something like that could be conceived?
I think that something like that would be possible and useful, surely. I think that maybe there are two problems. First of all, in the time span of my PhD, so to have time to set up the experiment, obtain the data, analyze them, and finally write the thesis, maybe it's little short time span to see an actual opinion evolution on some topic, because there are probably people that shift their opinion very quickly. They maybe need a few new information to change their opinion, or a few interactions to change their opinion, but there may be people that need a very long time span and a lot of information and context and interaction to change their opinion. So maybe the time span of my PhD would be a little short. And also, I think that people voluntarily taking part into the experiment may somehow bias their opinion towards, I don't know. I think that social network data, with all its problems, it's good because people nowadays are not really ashamed of expressing their opinions, their real opinions. So the gap between the expressed opinion and the actual real internal opinion is narrower than if we perform even anonymous questionnaires or anonymous survey data, because people still tend to be willing to express an opinion they think it's kind of correct to express. So some people may be changing the actual real data of their internal opinion.
That's a good point, yes. Second question, you mentioned that a potential interesting source of data is Reddit, right? And maybe you want to quickly, briefly explain, maybe there's other people interested, they don't really know maybe Reddit, and to what extent this can be good to your purposes.
Okay, so I think Reddit is a good source because it is a forum-like social media, so there is a lot of contribution to a specific topic. So for example, the data we are working on are from this subreddit are politics. So there are a lot of users participating in discussion on the topic of politics. So you don't need to perform analysis to understand the topic that users are talking about. You know, they are talking about politics. The drawback maybe of Reddit is that being a more like a forum than a social network, you don't know if there are actual social ties between its users. So you have an interaction networks of people posting and commenting on each other's posts, liking each other's posts, etc. But you don't know if some people maybe on another platform are actually connected or in real life are actually connected. For example, on Twitter, we have these social networks, so we can understand if interactions come from a social link or are induced by the platform algorithm showing some context, suggesting some content to the users. But of course, Twitter is less topic specific. So we don't have Twitter politics or I don't know, Twitter climate, Twitter environment. And so we need to establish a methodology to retrieve tweets about politics, which takes, of course, a little more time to do than just going on the subreddit politics. So I think that every social network, every social media has its pros and its cons when it comes to studying something like this. We started with Reddit because other researchers in the group were working on the same data and we're studying echo chambers, for example. And so we started from this 2 years time span data on politics, but we are planning to retrieve more data. We actually already have a longer time span of data. We plan on doing some more analysis on, and then maybe moving also to another platform, because of course some of the results we obtain may be also platform specific. So to generalize some conclusion on opinion dynamics or sociological theories, we need to see the same results cross domain and cross platform, of course.
Thank you. Any other questions or comments? Okay, it seems we are all somehow really striving for lunch. We are hungry, but I think it was really a refreshing morning of science. I really enjoyed it. Really thanks a lot to all the 10 PhD students that presented their ideas today. I think it's really a fantastic array of diverse topics that are diverse, but also very well connected by a thread that I think is evident to all of us. So really thank you for this. It shows, let's say, a health framework for data science and artificial intelligence. As I said, the next step now is to finalize the panels that will follow just the 10 students in terms of supervisors that are more or less set now, but also for the other people. And we will be contacting the board and the students with the request of explicitating which kind of panels you would be more interested to follow, so that we can before the break somehow have the panels set as a decision of the board, and we are ready to go for the evaluation of your PhD proposal that will take place in second half of September and October. Really, thanks a lot to everybody. The session has been recorded, which means that also the colleagues that could not attend will be able to see your presentations. I don't know if anything want to add anything. Let me thank everybody again. A special thank to Joanna Miliu and Vittorio Romano that helped me to organize all this day. I think it was very successful. Once again, thanks everybody and bye-bye.